Good afternoon, sir. Sujit, sir.
Yes, good afternoon, madam.
Sir, shall we start, sir?
Yes, madam, you can start.
1 minute, sir. Good afternoon, all. I welcome all of you to the day 8 of our program, Optimization Techniques, Theory and Practices and Emerging Applications. So today we are having two sessions. First session, Dr. Sujit Das sir is going to discuss about multi-objective optimization, and the second session, Sarath Naik sir will come. I think he will going to discuss about this higher order neural networks. So before starts this session, it's my privilege to introduce sir to our participants. So Dr. Sujit Das is currently working as an assistant professor in the Department of Computer Science and Engineering, NIT Warangal. He has awarded PhD from the Department of Computer Science and Engineering from NIT Durgapur. Sir has more than 18 years of rich experience in teaching, along with 9 years of experience in research with quality educational sector. He published more than 50 papers in the referred journals and conferences and scored more than 1500 citations. He has research publications in prestigious journals like Applied Soft Computing, Neural Computing and Applications, International Journal of Fuzzy Systems, Journal of Ambient Intelligence and Humanized Computing, Soft Computing, Journal of Intelligent and Fuzzy Systems, and many more. He is working as active reviewers in many reputed journals and conferences. Sir achieved 3 conference-based paper awards in CSO 2014, FICTA 2015, and the FORBS 2018. Dr. Das is a well-known resource person in the field of universal human values, which is required to nurture the human minds in order to bring the feelings of happiness in ourselves, our family members, and our society at the larger perspective. He has delivered a number of talks on universal human values in various workshops throughout India. He has organized a number of faculty development programs and conferences. Moreover, he has chaired many sessions in the prestigious conferences, delivered many talks as invited speakers in many FDPs, seminars, and conferences. His research interests includes fuzzy set, hybridized fuzzy soft set, multi-criteria decision making, robust and optimal solution using soft computing, artificial intelligence, evolutionary computation, and machine learning. So with this brief introduction, once again I welcome sir to our program, and it's over to you, sir. You can start your session.
Yeah, so thank you, madam. Thank you for this nice brief introduction. So really, it's an honor for me to share my thoughts on this nice platform. This really relevant topic today: optimization techniques, theory, practice, and emerging applications that is organized by ENICT Academy and NIT Warangal. So I'd like to express my thanks, special thanks to the coordinator of this FDP, Dr. Manjubala Mishimam and Dr. Sanjay Kumar Panda sir, for their invitation and giving me the opportunity. So with this, so I'm going to start the session. So am I clearly audible? So I want to ask the participants.
Yes, sir. Yes,
I
sir.
hope I'm
You are
clearly.
audible. Once you share your
Oh,
screen, sir.
oh, share my. Yes, I'm sharing my screen. Yeah, my screen is visible, madam.
Visible, sir. Visible, sir.
Okay.
Okay, sir.
Okay. So now thank you, madam. So let's start the session. So during the presentation, to avoid any distraction, so simply I'll switch off my video. And participants, please feel free to raise your queries. So during the sessions also, if you feel comfortable, you can ask me queries at the end of the sessions also. But I'll be happy if you interrupt me during my sessions. So as madam has already told, so this session is all about this multi-objective optimization and its applications. So once we are discussing regarding this multi-objective optimization and applications, so first we need to discuss, we need to say something regarding optimization technique. Although I believe that many of the resource person, they have clearly explained that what is optimization technique. So I will not go through in details. So optimization means in the simplest sense, so you can say that it is the process. It is the process to make something better. Just give me a minute. I will just use my device. Yes. Yes. So yeah. So optimization means in the most simplest manner, I can tell that it is the process of making something better. Now see the term. Here I am telling it is the process of making something better. But I am not writing it that it is the process of making something best. See, so difference is there between better and best. So none of the optimization techniques will guarantee you to get the best solution. Rather, all of the optimization techniques will guarantee you to get the better solutions. Then again, questions may be asked. If using the optimization techniques, once we are going to solve the problems, and if there is no possibility or almost very less possibility to get the best solutions, then why we will use this technique? Actually, for some of the problems, the complexity is so high, or some of the problems, sometimes all the information or complete information are not there. Whatever the parameters are there to formulate that problem, maybe all those parameters are imprecise, not precisely defined. So in those real life problems, it may be that if you work hard to find out the best solution, sometimes it may take so lengthy time. Again, sometimes what will happen that it may take some time, but again, there may be some very less chance to get the best solution. But once you are finding the better solution, it may be that within a fraction of a second, or very fast, very quickly, not within a fraction of a second, I should say very quickly, rather quicker manner, you will get that better solutions. Now, what is the difference between better and best? Suppose this is our search space. If we see that this is our best solution, then I can tell that this nearby points is my better solution. That means my better solutions are very much closer region to the best solution. So now this is the fact behind it, that optimization techniques, all of the optimization techniques normally gives us the better solutions. Two things are there. So sometimes we go for maximize our objective function. What is the objective function? So objective function means towards what criteria we are solving the problem. If our problem criteria is cost, then obviously we should minimize the cost. Then optimization problem will be minimization problem. But if your problem criteria is benefit, obviously you should go for maximizing the benefit. Then your problem will belong to the category of maximization. So once we are dealing with single objective optimization, so we can say that either we need to minimize or we need to maximize some objective function values. Now recently you will find out many meta-heuristics algorithms are there that we are using to solve these complex real life problems. Now these meta-heuristic approaches, so that are well-known part of any optimization techniques. What is meta-heuristic approaches? Those frequently we are using to solve those optimization problems. You see here two keywords are there. First keyword is the heuristic, second keyword is the meta. Once we focus on this heuristic approach, probably this may be the problem dependent or specific approach to solve a specific problem. But once we see the term, it is the meta-heuristics. Meta-heuristic means this is not problem dependent. That means using those meta-heuristics algorithms, you can solve a wide variety of problems. Just your task will be to map that problem to the corresponding meta-heuristic approaches. That's all. And that one important factor behind these meta-heuristics algorithms are these are biological inspired by this biological evolution process. Most important thing, most of the meta-heuristics algorithms are inspired from this biology. That means biological evolution process. Sometimes it may be inspired from the swarm behavior, sometimes from the physics law. That means what is happening surrounding us, So the algorithms are taking the ideas from those particular happenings or things those are getting around us, and simply trying to adapt those logic in terms of computational space, and we are getting some extraordinary algorithms. Now, how these meta-heuristics algorithms are getting these behaviors, or maybe the behavior that, so once ants are searching for their food, how the ants are searching for their food. If I drop one piece of sugar here, if I come after 2-3 hours, I will find out a long queue of ants are here. How it is possible? How they get to know that in my table I have placed some sort of sugar or some sort of sweets kind of thing. So if we follow that behavior of that ant, obviously that could be very much helpful for us to solve some real life problems. Also, if you closely look that how the flock of birds, they are searching for the foods. Once they are in the sky, flying in the sky, how they are searching for the foods. If you look closely, you will get to know that sometimes they are changing their positions among themselves. Based on that, they are, I think, again, based on the food source, or maybe they are changing their velocity, they are changing their positions. Actually, two concepts are there, local based and global based. So I'll not come to the point now. Anyway, so thing is that if we closely look, if we closely observe the behavior of the flock of birds once they are searching for their food, that means, again, if we apply similar kind of idea in terms of computational space, computational algorithms, obviously you will get a huge thing. And again, so it may be taking the ideas from some physics law. Physics law means what? Suppose I am heating a metal and then I am cooling it. Again, I am heating the metal, slowly I am cooling it. Again, I am heating the metal up to some temperature, slowly cooling it down. What will happen? Metal strength will be more. See, so if we apply again this process to solve our day-to-day problem, so that will be the nice thing. So meta-heuristic approaches, simply they are adapting the ideas, what is happening in the nature surrounding us. Now, these algorithms we can broadly classify into two categories. One is single solution based, second one is population based meta-heuristic. Two things, single solution based and population based. So what is the difference? Single solution based meta-heuristic means it will start from a single solution. It will start from a single solution and then it will gradually move to upgrade that particular solution's quality, and in that manner it will explore the search space. Search space means what? Search space means we assume that inside the search space we have all the feasible solutions. Now, what is population-based meta-heuristics? So in case of population-based meta-heuristics, instead of considering a single solution, we will consider a multiple number of solutions like that. Instead of considering a single solution, we will consider a multiple number of solutions. And we will do some operations, do some tasks on those solutions, so that once we will move from this generation to the second generation, average solution quality will be improved. See, that's the situations. Population-based meta-heuristics. We have started from this generation with this number of solutions. If we move to the second generation by implementing some sort of operations, then in the second generation, suppose here 6 number of solutions here. So in the second generations, we will get exactly the 6 number of solutions. But what will be the difference here? Difference will be that the average solution quality will be much more updated. You may be wondering to know it, that how it is possible once we are moving from first generation to second generation. So how average solution quality is becoming more. Here, one thing I should say, I am telling that solution quality, how to express the solution quality. So we can tell a fitness function. So using those fitness function, we can express the solution quality. If we are solving maximization problem, so if fitness function or fitness value of a solution is more, that means obviously that is the higher quality solution like that. So that means fitness value we will consider to denote or to identify or to determine the quality of a solution. So this is the difference between single solution based meta heuristics and population based meta heuristics. Today, this population based meta heuristics, that will be our topic of discussions. We'll find out how this solution quality will be improved once we are moving from one generation to second generations. Now, under this population-based meta-heuristics, again, two things are there: evolutionary algorithms and swarm intelligence algorithm. Today, mainly we will focus on this evolutionary algorithm part. So, evolutionary computation, as I told, evolutionary computation means, so that is a family of these global optimization algorithms that are inspired by this biological evolution. And I should say that, I must say that this evolutionary computation, that is a subfield of artificial intelligence and soft computing, which are a very much relevant topic today to solve these real life problems. So as already I told that in evolutionary computation, initially we will start from a set of candidate solutions. Each and every solution I am writing as candidate solutions. So that means initially we have a set of candidate solutions. What will be our task? To iteratively update the solution quality in each and every generation. The most important factor is, yes, how to do that. That only we are going to discuss in next half an hour. So today I have divided my this discussion in two parts. Firstly, I will give an overview of you regarding that genetic algorithms very quickly, very fast, to the next half an hour. Next, I will try to move in details regarding this multi-objective genetic algorithm that is called MOGA. More specifically, today I will tell regarding NSGA2. Okay, so NSGA2, that part today I will discuss in detail, probably using some case study. And you know, tomorrow again I have one more session. So tomorrow what I will do? Today whatever I will discuss, genetic algorithm and NSGA2 particularly. So tomorrow I will try to implement using Python programming language both the things. That's why today whatever we are discussing, it's very much necessary for the participants to understand it very clearly, so that in our next session, quickly we can write the corresponding programs using Python programming language. Okay, so whatever we are discussing here, again coming back to the topic. Yes, so evolutionary computations. So as I told that evolutionary computations, so that is mainly two important things are there in evolutionary computations. One is the genetic inheritance and second one is the natural selections. Most two important criteria of any evolutionary computation is genetic inheritance and natural selections. How it is using this genetic or applying genetic inheritance, how it is applying natural selection. You know, if we look closely what is happening in the nature, I think I can tell one thing. So if we ask someone that, okay, tell me that all the giraffes having long neck today, giraffes has always long neck. It is true or false? Obviously, I hope that most of the participants will answer, sir, it will be true only. Because whatever the giraffes we are finding surrounding us, long neck only. But believe me, that statement is false. Because what is happening here? So giraffes with long neck, they are surviving mostly because so they are adapting in the nature as they have the high neck. So that means long neck. So they can eat the upper leaves from the upper branches of any tree. But what will happen with giraffes with short neck? What will happen with giraffes with short neck? So giraffes with short necks has a very less chance or less probability to survive, because once the leaves from the shorter, from the less, I think, yeah, from the shorter branches, that will be over, then they will face a challenge to survive. But can I say that giraffes with short neck has a zero probability to survive? We can never say. You say that. By chance factor, giraffes with short neck, I should say, has a non-zero probability to survive. But giraffes with higher neck, giraffes with long neck, they have much more probability to survive. See the situation. This is the natural selection. That means who can adapt to the changes in nature, they will survive. Who cannot adapt the changes in nature, there is a non-zero probability to survive for them, but survival chance is very less. So this is the natural selection. Okay, and what is that genetic inheritance? You know, so common assumption or common thoughts are there. If parents are there better, then their offsprings are supposed to be better. Their children are supposed to be better. So that means if of the children are having, they are taking some properties from their parents, as well as they are having their own properties, own features. That means if parent solutions are better, see, so if parents, suppose these two parent solutions, so if parent solutions are better, P1, P2, so if we apply some kind of mating process on these parent solutions, then as a result, we will get two offspring solutions, S1 and S2. So what will happen in turn? If parent solutions are better, obviously these offspring solution has a high probability to be better. But exceptions are also there. But this is the genetic inheritance. So that part we will try to apply in our genetic algorithm. So mainly two things. One is natural selection, second one is the genetic inheritance. Yes. So again, before coming to the genetic algorithm, again, I must say one thing, that genetic algorithm, they have the ability to deliver good enough solutions in a fast enough manner. Not only genetic algorithm, all the optimization techniques having the capability to deliver a good enough solutions in a fast enough manner. I'll call you after some time now in a talk. Okay. So what does it mean? Suppose at some moment I am traveling some place which is my unknown place. I want to visit from some place to some other places. What immediately I will do? Obviously, I will take help of GPS navigation system. And GPS navigation system, what it will give us as a result? So some path. Very fast, very quickly it will give. Now tell me, so that path, it is the best path or it is the better path? Obviously, if you look closely, that path, whatever you are getting by searching GPS navigation system, that path is always the better path. That means, so if you are waiting for the best path, that means it may be your GPS navigation system will take a long time. So long time that ultimately once you reach to the destination, there will be of no use. So this is the main motivation behind genetic algorithm. Good enough solutions in fast enough manner, which is really, I think, very much beneficial in our day-to-day real life. Okay, now let me come to the fact of this genetic algorithm very quickly. So population, you know, population means what? Population means the set of possible solutions. Those are called population. And each and every solution is said to be chromosome. How these things are coming? Chromosome, since it is a genetic algorithm. So that's why we are using some terms from this biology, chromosomes. And you know, so each and every solution I am telling as a chromosome. So what will be the parameters of each and every solution? Those parameters are said to be gene. Once you are solving some problem, obviously each and every problem will having some parameters. So these parameters are nothing in terms of genetic algorithm. We will consider those parameters are a gene. Now again, two concepts is there. One is genotype, second one is phenotype. You know, once we are discussing the problem in our real life, that is called genotype. And once we are mapping the problem from our real life to the computational space, that is called genotype. It's earlier called phenotype. Suppose we are going to solve a traveling salesman problem. I hope all of you know the traveling salesman problem. That means some cities are there. Okay, some salespersons are there. So objective of the salesperson, that means start from a city, will visit all the city, maximum one time, except the initial city. where you will start the visit and complete the visit. Objective is that either to maximize the profit or to minimize the cost once the salesperson is traveling through all these cities. So once we are discussing regarding this traveling salesman problem, so that means we are discussing the problem in the phenotype space. Once you want to solve this TSP problem, okay, using genetic algorithm, then how you are mapping the TSP problem in terms of genetic algorithm, that is known as genotype. So each and every problem you should encode from phenotype space to genotype space. Once you complete your task, once you got the solution, then again you should move from this genotype space to phenotype space. That is called decoding. So already I told you regarding the fitness function, what is known by fitness function. Yes, next gradually I will move quickly to that fact of genetic algorithm. So again, I should say that genetic algorithm that is inspired by this Darwin's theory of natural evolutions. Organisms that are poorly suited, they will die off. Well suited, simply they will prosper. Okay, now let me say you something regarding this genetic algorithm. So before proceeding, so here, this is our search space. Suppose these are, okay, suppose fitness value, this is 30, this is 40, suppose this is 5, let us say. So number of solutions are 4 in our first generation. So once we will move to the second generation, obviously your number of solutions are fixed. So that will be 4 only. Now, how to implement the natural selection? As I was telling, so the solutions which have the higher fitness value, that means good quality solution. What natural selection is telling that those solutions will be copied in more number. And there is a very less chance of those solutions for which the fitness value is less to be selected. Selection chance is very much less. So let us assume here 40, we are getting 2 copy of this 40. Okay, let us assume that we are getting 1 copy of this 30, as well as we are assuming 1 copy of the, we are getting 1 copy of that 20. See, this is called natural selection. Solutions for which quality is more, that will be copied in more number, and quality is less, that will be copied in less number. Okay, so now our natural selection is over. Later we will see that how to implement this natural selection using our computational approach. Next, what is our task? So next our task is that, now you see, so immediately after the natural selection, if you find the average fitness value, then average fitness value, here it will be more than this. After natural selection, obviously, average fitness will be much more higher than that initial generation. Next, what you will do? You see. So as I told, next we want to implement some kind of inheritance kind of things. That means, suppose randomly we are selecting some couple of solutions. Let us say randomly we are selecting 20-40 and 30-20. Randomly selecting. Then what I am doing? Then I am implementing some kind of matching process on those solutions. As you know, so after the matching process, whatever you will get, again you will get from these 2 solutions 2 offspring solutions. Maybe here it is 42, maybe it will be 45. Maybe this one it will be 25, maybe this one will be, suppose it is, maybe it is 29. What you are getting? Again, so after implementing that kind of mapping on the randomly selected couple of solutions, then as a result, what we are getting? We are getting that average fitness value is again improving. See the importance. The simple fact, what is happening in the nature, the same thing we are adapting in our algorithms. And as a result, in each and every iteration or generation, our average fitness value is getting improved. So why not? That kind of fact we should adapt in an algorithm that is known as genetic algorithm. So genetic algorithm is simply adapting these ideas, what I told right now. Yes. So algorithm, it will start from initial set of solutions, that is called population. Actually, what I told. Then what it will do? So each and every solution is known as a chromosome. Chromosome is a collection of genes. Okay. Yeah, see. Solutions from one populations are taken and used to form new population by generating the offsprings. How you will generate offsprings? So by that mating process. And that mating process, in terms of genetic algorithm, it is known as crossover. Okay. So new population is formed from the old population and offspring based on their fitness value. See, promising candidates are kept and allowed to reproduce. See that. Promising candidate means which candidate? Obviously, those solutions which are good quality solutions, or for those solutions which is fitness value is more. Why? Why you can do that? This is motivated by hope that new population will be better than the old one. Obviously, after the natural selection, what we have seen after the natural selection, we are having some more good quality solutions. If we apply some kind of crossover or mating process, so again, as a result, whatever the offspring solution we will get, those average fitness value will be more. Yes. Now, actually, what I told, so that thing is depicted here in this flowchart. This is the flowchart of genetic algorithm. Create a population of chromosomes. So this population of chromosomes we are creating, determine the fitness value. This is 5, 10, 15, 20, suppose. Then next generation, that means we'll do some natural selection. As you know, after implementing natural selections, so the solutions which are having more fitness value, they will be copied in more number, and less fitness value, they will be copied in less number. Then perform reproduction using crossover. Just now I told. We'll randomly select a couple of chromosomes and we will implement the crossover. That is one kind of mating process. As a result, again, we will get some set of solutions. So the idea of crossover is that if you select two randomly chromosomes, then as a result, you will get two offsprings. From a set of two solutions, we will get two offsprings only. What will happen? Again, as a result, the fitness value will be improved. Okay, so here the fitness value is again getting improved. So as a result, you will find out total average fitness value is improving. Then we will implement mutation. What is mutation? Mutation means sudden changes in gene. So later I will tell you what is the actually in-depth thought regarding this crossover and mutation. Suppose this 12, okay, this is the fitness value of some solutions, this one. Mutation. So if we perform mutation, that means we are changing some genes randomly. Then what may happen? Then it may happen this solution, fitness value of these solutions, it may be much more improved. Chances are there, fitness value of the solution may be reduced also. But why you will do that? Why mutation is necessary? You know, so if this is the search space, once you are applying crossover or mating process on these two solutions, then as a result, you are getting two offsprings. Then it is assumed, or it is more scientific, that the offspring solution will be very much closer region of the parent solutions. That means it will not help you to explore the search space in detail. This is the search space. Many solutions are here, there. Our target is to find out the optimal solution. But if you limit yourself in a closed region, then it may not help you to search the other solutions. Because as a crossover, what I am telling, so it is getting the solutions which are very much closer to the parent solutions. But in case of mutation, since you are randomly changing some set of genes, then from this solution, directly by implementing the mutation, it may come probably to some high, long, far distant solution. From here, you may reach here. That means, obviously, mutations will allow you to explore the search space much more healthy manner rather than the crossover, which is very much required to come out from the concept of local optima. I hope you know the concept of global optima and local optima. Global optima means globally based, local optima means locally based. So this is the global optima and this is the local optima. If you are at that point, then your solution may feel, your process may feel, okay, if I move right, move left, so my fitness value is decreasing. That means maybe this solution is the best solutions, or I have converged, I have reached to the target. Is it like that? So this is not like that, since this is the global optimum. So actually, so it is not the crossover, it is the mutation that will help you to come out from the local optima to move towards the global optima. See, so our mutation is over. Come back to the flowchart. Our mutation is over. Then again, we will repeat the process. We will determine the fitness of each and individual, select next generation. These things again we will continue. So this is the flowchart behind this genetic algorithm. When should we stop? It may be that after some successive generations, consecutive generations, you will find that your changes in the average fitness value is very much negligible. What is the average fitness value? The changes in that is very much negligible. Probably that is the right place to stop. That means you may feel that your algorithm has converged. It got the desired solutions. Okay, so more or less we have discussed the basic structure of genetic algorithm very quickly. Then I will answer some questions. Then we'll move to that multi-objective part. Now, how to create the chromosomes? What type of encoding to use? In the simplest manner, I told you that is chromosome. How to use chromosome? What are the encoding techniques to be used? How to perform crossover? The mating process I told you, that is called crossover. How to perform it? How to select parents for the crossover? Now let us see quickly, I will tell. So this is the encoding of a chromosome. So many techniques are there. One of the important techniques is that binary encoding format. Each and every solution that we say as a chromosome, so that can be represented the sequence of zeros and ones, bits of zeros and ones. Now, how many zeros and ones will be there? That depends on the number of parameters of the problem. Parameters means nothing, number of genes in that particular problem. That will identify the length of that particular chromosome. Now, you can ask me, sir, for which set of problems this binary representation may be helpful? So for those set of problems where you can represent the problem parameters in two values, either 0 or 1, either true or false, only that kind of problem, this binary representation or this binary encoding technique may be much more fruitful. I can tell you one problem, that is the knapsack problem. If you solve the knapsack problem, obviously you can represent the chromosome using this binary encoding format. Okay, now we'll come to that part, that selection. So once we have got the chromosome, here what we have done, we have computed the fitness value of each and every chromosome. What it will give the fitness value? As I said earlier, it will give the quality of the solution. That's over. So that means we have got some solutions as well as we have computed their fitness value. Then we need to implement natural selection. We need to implement Darwin's theory of survival of the fittest. So how to do that? As I said, after implementing natural selections, more copies of good solutions will be there and less copies of poor quality solutions will be there. How to do that? So for that purpose, many techniques are there: proportional selection, Rowlett-Hewell selection, tournament selections, and many other approaches are there. Today, quickly I will tell you Rowlett-Hewell selection mechanism. What is the Rowlett-Hewell selection mechanism? Let us assume three solutions are here, A, B, and C. Fitness of A is 3, fitness of B is 1, fitness of C is 2. Okay? So, if you compute the probability, here you will get that solution A will occupy 50% of the Rowlett-Hewell. Solution B, 1 by 6, it will occupy 17% of the Rowlett-Hewell. Similarly, C, occupy 33% of that Rowlett-Hewell. So actually you are getting that which solutions are occupying more. Obviously, the more quality solutions, the higher quality solutions occupying more space in the Rowlett-Hewell. Now let us take this point. Spin the wheel. I am asking you to spin the wheel 5 times. And see here, in this point, which solution is coming? Just to take that solution. Now tell me. Here, taking or getting solution A, probability of getting solution A will be more. Probability of taking solution B or selecting solution B will be very less. Your solution may become like that. A, then suppose I am telling B, C, C. It may be like that. If you consider 6, again it may be 1A. That means, see, this is the natural selections. How we are implementing the same thing technically using this Rowlett wheel. Solutions which are of more high quality, that will be selected in more number. Solution which is of very less quality, that will be selected in very less number. We are not doing randomly. So actually using this Rowlett wheel, we are getting the same fact, exactly the similar thing, whatever the concept we are getting from that natural selection. Tournament selection is okay, we will skip. Okay. Now, one important concept behind genetic algorithm, that is the elitist model of the genetic algorithm. Suppose I am telling you in this search space, once you are having a population of solutions, suppose here this solution fitness value is 100. Here it is 5, here it is 10, here it is 15. Now you tell me. So if you incorporate this solution A, which is very much higher fitness value in the crossover technique, in the matching process, then what will happen? If we apply crossover between these two solutions, then what may happen? That means the solution quality may lose its characteristics. Better, once if we find some solution in some search space has some exceptional quality solution, then instead of implementing any operations on that solution, directly move that solution to the next generation. So this is known as the elitist model of genetic algorithm. That is very much important to make our convergence very much faster. Otherwise, what will happen? So that solution in the process, once we're implementing crossover, mutation, so it may lose its characteristics. Okay, I have told so many things regarding crossover. Now it's the right time to little bit explain what is crossover. Crossover means partial exchange of information between two randomly selected parent chromosomes. See, suppose this is the parent solutions, okay, parent 1, parent 2, and this is our offspring solutions. What it is happening? Just it is exchange of information. See here. So here we need to select a crossover point randomly. So this is the randomly selected crossover point. Next, exchanging the information. These informations we are keeping here, and these informations we are simply keeping here. Exchanging of informations between two randomly selected parent chromosome is called as crossover. So this our thought is this is very much similar to the mating process. Okay, so our assumption is that in crossover, if we consider two parent solution, as a result, we will get two offspring solutions. So how? Okay, so this is the crossover. So using if we consider the binary encoding technique, then this will be the example for the crossover. See here, these are two parent chromosomes. Okay, after implementing the crossover, we are getting these two offspring solutions. Information interchange. This information simply we are keeping here, and this information like that. So after that crossover point, so from chromosome 1, it is copying to offspring 2 like that. So simply this information is to here. So exchanging the informations between two randomly selected parent chromosomes. Okay, now what is mutation? As you can remember, mutation I told that is random changes in gene. Now how many genes will be selected? We don't know. Now maybe 1 genes, maybe 2 genes. Again, that can be selected randomly. See here. So for crossover, we need a couple of solutions. But for mutation, we don't need a pair of solutions. Consider this individual solution of spring 1. See here. Randomly, I have selected this position. Then after implementing the crossover, what is happening after implementing the mutation? So in the mutated offspring, so this 1, this is changing to 0. See. In offspring 2, let us say These two are the genes I have randomly selected. That means this 0 is becoming 1, this 1 is becoming 0. So that is the example of mutation once we are considering binary encoding format or binary encoding technique. As I was telling again, crossover, we need couple of solutions, pair of solutions, but for the mutation, we don't need that. Okay. Randomly one chromosome may be selected after crossover, and then you need to implement mutation on that randomly selected chromosome. Again, you can ask me that how many number of times you may implement crossover and how many number of times you should implement mutation. Normally, crossover probability is much more higher than the mutation probability. What is crossover probability? The number of times you need to implement crossover is known as the crossover probability. Number of times you need to implement mutation, it is known as the mutation probability. Okay. Yeah. So termination of genetic algorithms, already I have told that many termination criteria are there, but that will be the, I think, the most suitable one once you move through some successive generations. And if you feel that your average solution quality or average fitness value is not improving, almost it is fixed, it is constant, then probably that is the right time to terminate your genetic algorithm. Now, these are some application scopes of genetic algorithm. Countless number of scopes are there. We can apply machine learning with genetic algorithm. We can apply some AI techniques, also some data science also using this technique. Okay, so now we have more or less in this 45 minutes or 50 minutes, we have discussed, we have got an overview of genetic algorithm, of single objective optimization techniques. Single objective, that means we are satisfying working with one objective only. Once you work with the traveling salesman problem, your objective is one, either you want to minimize the cost or you want to maximize the benefit. Are you working on those two objectives? Both, you will minimize the cost as well as you maximize the benefit? No. Once you are working on the single objective genetic algorithm, it is known as single objective. That means you are working on one objective only. But believe me, whatever the problems you will feel, you will see in nature surrounding you, most of the problems are of multi-objective in nature. Rarely, very hard to find some single objective problems. Almost all the problems are multi-objective in nature. So that means we should know how to deal with these multi-objective real-life problems. See, multi-objectives, more than one objectives, and obviously the objectives are conflicting in nature. So this is purely for experimentation purpose. So if we want to buy a car, so obviously two things are there. One is comfort, second one is cost. If you want more comfort, so what will happen? Our target is that, intention is that comfort should be more as well as cost should be less. See, these two objectives always conflict, but you should not postpone our decision. We should take some decisions. Then how you will take the decision? So to take the decisions, once you are buying a car, obviously you should know the multi-objective optimization concept. Obviously that will help you to get some solution. Yes. So, so in single objective optimization, so once we will get some solutions, so a set of solutions as a result. So similarly, in multi-objective optimization problem also, so you will get a couple of solutions as a result. See here. So that part again, at the end of the sessions, I'll tell you that once we are discussing regarding multi-objective optimization problems, so once you are solving it, as a result, you will get a set of solutions, not a single solutions. Okay, you will get a set of solutions. So once you are getting a set of solutions, then how will you prefer which solution you will identify for you? Actually, this multi-objective optimization problems, it will give you a group of solutions or a set of solutions instead of a single solution. Now, from our domain knowledge, we need to select that for which solutions we are preferring. Obviously, that part I will explore. Just wait for that. Okay. Yes, so multi-objective optimization problem. Yeah. So if you want to improve in one objective, obviously it will degrade in another objective. If you want to improve the comfort of the car, obviously your cost of the car will be more. If you want to degrade your cost of the car, so what will happen? Comfort also will be degraded. So similarly like that, most of the real life problems are multi-objective in nature. See that minimize time and cost for travel. See this example. So this is the time taken and this is our economy level. So if we start walking, obviously economy level will be very less, but time taken will be more. If we start cycling, little bit improved. That means time taken little bit less at this moment. At this point, economy level little bit improved. If you take horse, economy level little bit improved. Time taken little bit less. Similarly, bike. Similarly, this car. See the situation. What is happening here? Okay, suppose now I am giving you one more car. Now tell me. So if we compare between these two cars, then which car you will select? By applying the concept of multi-objective optimization problem. See here. Our objective is to minimize the time and cost both for travel purpose. See. So for this, just yeah. See. So for this smaller car, time taken is this. Okay. Economy level for the both small and big car is same. Let us assume. But time taken for this bigger car is little bit less. Obviously, we'll go for the bigger car. See the situation. Obviously, we'll go for the bigger car. How? What is the concept is there behind it? Let's see. So in terms of the economy level, most of the cars having the same value. But in terms of the objectives time taken, bigger car is much more improved regarding the smaller car. Here the concept is that bigger car is said to dominate the smaller car. You know, in multi-objective optimization problem, the concept is there, concept of domination. Dominating, so this solution dominating this solution. When you will say in multi-objective optimization that one solution dominates other solution. So keep remember this particular idea. Again, we will come to that part, the definition of dominance. Okay. Yes. See, single objective optimization problem superiority of a solution can be determined by objective function value. How much a solution is superior than other solutions. You can easily determine using the objective function value. But once we are discussing regarding this multi-objective optimization, it is the dominance, degree of dominance. Goodness of a solution can be determined by this degree of dominance. We'll understand this degree of dominance in detail in our next few slides. So it is different. Multi-objective optimization. We cannot say that this solution objective function is more than that. How we can tell? Because multiple number of objectives are there. Simultaneously, you need to take care of the multiple number of objectives. How it is possible? If you do some improvement in one objective, what it may do? It may happen degradement in the other objective functions. So based on that, you should select your solutions. Now let us proceed. Okay, we'll find what is domination. We'll see. We'll see what is dominations. Yeah, let us first discuss the concept of dominance. That I'll come to the other concept. Yes, degree of dominance, multi-objective optimization problem. Goodness of a solution is determined by the dominance. I think from this example, you will go to get to know what is the dominance kind of things. See, x1 is said to be dominated, or x1 dominates x2, or x2 is said to be dominated by x1 when. This is the criteria. x1 dominates x2 if solution x1 is no worse than x2 in all objectives. Solution x1 is strictly better than x2 in at least one objective. If this thing happens, then we can say x1 dominates x2, simultaneously x2 is dominated by x1. See the situation. x1 is not poor than x2 in all objectives, but solution x1 is strictly better than x2 than at least one objective. Let us come to our solution, what we discussed earlier. This solution is better than this solution, bigger car is better than the smaller car, at least one objective, at least for the time taken. This objective, smaller car is better than, bigger car is better than the smaller car. But for other objectives, that is the economy level, my bigger car is not poor than the smaller car. Check it very clearly. My bigger car, so my bigger car has, I think, in terms of the fitness value, in terms of the economy level, my bigger car and smaller car is similar. But in terms of the objective function time taken, my bigger car is better than the smaller car. Then I can say solution x1 dominates x2 if solution x1 is better rather than solution x2 for at least one objective function. And for other objective function, it should not be poor than that x2. Then we say, so this is the, then x1 dominates x2. Let me show you some more example, otherwise it may not be clear, which is very much required for us. So let us see. So this is F1 objective, that is for maximization purpose. This is F2 objectives, that will go for this minimization purpose. Okay. Now, solution 1 versus solution 2. This is our solution 1, this is our solution 2. Take it very clearly. Here I will say that solution 1 dominates solution 2. How I can tell? See, in terms of objectives F1, see, which target is to maximize if 1 has more value rather than 2. Okay, in terms of F1 objective. Okay, 1 is better rather than 2. Now, in terms of F2 objective, why it is to minimize? Again, 1 is better rather than 2. That means in terms of both the objectives, F1 and F2, 1 is better than 2. Here we can say that 1 dominates 2. Try to get it. Again, our example 2, 1 versus 5. Check it. This is 5, this is 1. Quite interesting. So 5 is better than 1 in terms of F1 objective, because 5 touches here, 1 touches here. So 5 is better than 1 in terms of F1 objective. But both 5 and 1 are equal in terms of F2 objectives. See, that means 5 is strictly better than 1 in terms of one objective, but solution 5 is not poor than 1 with respect to all other objectives. If this is the case, then we can say 5 dominates 1. I hope now you are getting it. So we will try to explain it using another example. 1 versus 4. Check it. 1 versus 4. 4 is better than 1 in terms of F1. But 1 is better than 4 in terms of F2. That means our idea or our degree of domination is not applicable here. If this is the case, then we can say that neither solution dominates. That means 1 and 4 belongs to the category of non-dominated solutions. Neither one dominates others for solution 1 and 4. Okay. Now this is the dominations what we have already discussed. Solution P dominates solution Q if all objectives of solution P is not more than that of Q. but for at least one objective, P is better than Q. If this is the case, then we can say that P dominates solution Q. Here, whatever we will discuss, all the optimization problem, we will consider as the minimization problems. Okay. So before that, yeah. So this was an important thing. Yes. So see. Now, how we are converting from our simple single objective GA to multi-objective GA? See here. So single objective GA, we focused on this fitness function. So in the multi-objective GA, what we are trying to do? Simply, we are modifying the fitness function. We are modifying the fitness function in terms of dominance. And we are trying to emphasize on non-dominated solutions. I think here now you are getting the point, domination and non-domination. When a solution is said to dominate others, when it is said it is not dominating others. Okay, so initially we'll focus on this thing, non-dominated solutions. Once we get some kind of non-dominated solutions, then we'll focus on this crowding distance that I will say later. Crowding distance. So from the non-dominated solutions, we will select those solutions which are very less crowdly, actually less crowdy, that are computed using crowding distance mechanism that we'll discuss later. But here it is the way how we are transforming from the single objective GA to multi-objective GA. Yes, now this is the definition for this non-dominated solution set. Take the definition. Later I'll give you some examples. Non-dominated solution set is the set of solutions that are not dominated by any other in the solution set. Term is itself non-dominated. That means non-dominated solution sets are not dominated by any other solutions in the solution set. And this non-dominated set of solutions, those are known as Pareto-optimal set. And this boundary formed by this Pareto-optimal set, this is known as Pareto-optimal front. Actually, in case of multi-objective optimization, our target will be, we should be as much as closer to the Pareto-optimal front. So that should be our target. These are some definitions. So I hope you are getting that non-dominated set, what is Pareto-optimal set, what is Pareto-optimal front. Again, we will discuss some examples, then it will be much more clear. Let us say, once we want to buy some car, so if we focus on the single objective optimization problem, someone may go for objective speed. Okay, we want to maximize the speed. But if you maximize the speed, if your objective is on speed only, then what might happen? You might feel poor riding concept, poor handling, expensive, poor fuel efficiency. It should be unsafe also. So should we go for the objective speed, single objective optimization? Once we are thinking to purchase some car, or no, we'll go for multi-objective. Obviously, we'll go for multi-objective. That means here we want that the speed should be more, comfort should be more, handling should be good, price. This should be less. Fuel efficiency should be more, safety should be more. So that means, see, this is that multi-objective optimization problem. We want everything, but at the same time, we want price should be low. Let us discuss more clearly using some examples. See, here instead of taking all the objectives, I have considered two objectives to make our problem simple. Objective 1 is speed, objective 2 it is handling. So this is the population. Here we have considered 1, 2, 3, 4, 5 set of solutions. Okay, let us say for this solution A, car A, speed is 60, handling is 40. For car B, speed is 20, handling is 80. Similarly for the remaining cars. Okay. So these things are given for multi-objective optimization problem. And for single objective optimization problem, if you are considering only on speed, so this is given to you. That means, okay, based on single objective optimization problem, it will take only hardly few seconds to decide which car we will buy. But if we go for multi-objective, then it is very much difficult. Let's see. Obviously, In single objective, so we'll go for purchasing the card D since speed is maximum. Now see what happens. If you go for card D, if you consider multi-objective, then what is happening? Speed is more, but handling is so less. That means it is not going to be comfortable for you in near future. So we should not go for this single objective based optimization problem. We will move to this multi-objective only. Now let us see. Yeah, let us see. Now, if you consider, I want handling should be more, then what is happening? If handling is more, that means maintenance, you want a good maintenance kind of things, then what will happen? Your speed will be less. It's, I think, a huge trade-off I am getting. These two objectives, speed and handling. So how to take some decisions? Now let us proceed further. So here, whatever right now I have told, the entire thing I have plotted in a graph. Okay. So this is my car A. See that? Speed 60, handling 40. So this is the speed, x-axis, y-axis is the handling. So see the situation. So this is my car A. Now see, this is car B, speed 20, handling 80. See, car B, speed 20, handling 80. This is my car B. Similarly, I have plotted the cars. So see the cars C. The speed is 10 and handling is 40. Like this. Whatever the values I am getting here, so all these values I have plotted in the graph to take some decisions. Okay, let us proceed. Okay. Now here we will try to incorporate the concept of dominations here. Okay. Now, so can you tell or what will be the domination relationship between C and D? Can you tell which solution will dominate and which solutions will be dominated? Is it like that B is dominating C or C is dominating B? Take it very carefully. This thing we need to say based on the idea of domination, whatever we have learned right now. So our objective is that speed should be more as your handling should be high. This is our objective. That means for B, speed is 20, handling is 80. For C, speed is 10, handling is 40. That means for both the objectives, B is much more improved rather than C. Then I can say solution B dominates solution C. Take it here. So that means if two options are given to you, solution B and solution C, car B and car C, obviously you'll go for car B because car B dominates car C. Now what is the relation between E and C? Again, same thing, C. So this is the speed of solution E, 40, and this is the speed of solution C. That means solution E is better than solution C in terms of speed. Now this is the handling of solution E, 50. This is the handling of solution C, 40. In terms of handling also, solution E is better than solution C. What is your conclusion? So in terms of both the objectives, speed and handling, solution E is better than solution C. That means solution E dominates solution C. Is the situation. That means if three solutions are given to you, three cards, C, B, and E, obviously you should reject C. But between B and E, check it, between B and E, what will happen? Okay, I'll come to the situations. Now let us see. Solution A. Again, the same thing. Solution A will dominate solution C. So, in that manner, so if we find out the situations, then what is happening? Let's see. As I told, solution B dominates solution C. Solution E dominates solution C. Solution A dominates solution C, as well as solution D. Now see here. So what is happening here? Check. That means, so easily we can drop car C or solution C from our list. Okay. What about the remaining things? B, E, A, and D. What about the remaining things? B, E, A, and D. So can you compare between B and E in terms of dominance? Can you compare it? Okay, let me make it very clear. Sorry. Can you compare it? Just a minute. Yeah. So can you compare between these two solutions, B and E, in terms of domination? Let us check. E 40, B 20. E is better in terms of speed, but in terms of handling, who is better? In terms of handling, B is better rather than E. So there is no domination relationship between B and E. Similarly, between among B, E, and A, no domination relationship. If we consider more, A also, D also will be in the list. That means B, E, A, and D. So you cannot compare in terms of domination. That means these set of solutions are said to be non-dominated set of solutions. This set of solutions is said to be non-dominated set of solutions because none of the solutions in the solution set are dominating this set of solutions. Rather, a non-dominated solution set dominates all other solutions in the solution space. So now, non-dominated solution set means these four solutions, it will form the Pareto-optimal set, and whatever I have shown you, the boundary. This boundary may be called as Pareto-optimal front. I hope now the concept is very clear. What is non-dominated solutions, what is Pareto-optimal set, as well as what is Pareto-optimal front. Yes, non-dominated solution set that we are discussing. So none of the solutions in the non-dominated set is absolutely better than other. Any one of them is an acceptable solution. If I ask you from this non-dominated set of solutions, which solutions you will prefer? Each of every solutions is a solution here. A, B, C, D, E. All the solutions in the non-dominated sets are some preferable solutions. As I was telling, multi-objective optimization will never give you a single solution. Rather than it will give you a multiple set of solutions. Then what? That means now you should have some domain knowledge that which solution you want to prefer among these set of solutions. That it is written here. None of the solutions in the non-dominated solution set is absolutely better than other. We cannot say no domination relationship. So one of them can be selected as a acceptable solution. Now this choice of one solution over other, this requires the problem knowledge and a number of problem related factors. So some domain knowledge is required to find out which solutions you will prefer among this number of solutions. Now, so one solution chosen by a designer that may not be acceptable for other designers, as I am telling, entirely depends on the domain knowledge, which solutions you are getting to prefer. But yes, all of the solutions are treated as a perfect solutions there because none of them are dominating each other. Now, this is the mathematical formulation for this single objective optimization problem and multi-objective optimization problem. See, single objective, only one objective is there, one objective function. But for multi-objective optimization problem, F1, F2, F3, Fk, a number of objective functions are there, subject to some constraints. So they are the constraints you need to satisfy for both set of solutions. But this is the mathematical difference. Only single objective functions, and here multiple number of objective functions are there. Okay. Now here important study is there that is known as Skeffert study for this multi-objective optimization problems. See here, if you look closely to the study, see what is your objective function. Our objective function is to minimize x square as well as x minus 2 square. Okay, so this is our x-axis, this is x square, this is y-axis, this is x minus 2 whole square. Our objective is to minimize both of these. Try to make it very clear. So where this is our range, x may lie, x may belong. Now let us see. Let us start from here. If x is 0, then x square, what is x minus 2 square? X is 0 at this point. So that means what will be the value for x square? X square, it will be 0. X equal to 0. What will be the value for x minus 2 square? It is 4. So this is x equal to 0. These are two values. Try to get it. Okay. So once x equal to 1, what will happen? X equal to 1 at this point, x equal to 1. That means x square, it will also will be 1, as well as x minus 2 square, it is also 1. As per this, I am not taking it randomly. Take it. So as per our objective function only, x equal to 1, x square equal to 1, x minus 2. This value also will become 1. 1 minus 2 square minus 1 square, that means it is also 1. So that means this is the point. Okay. Once x equal to 2, then x square equal to 4. See, x equal to 2. So x square equal to 4. And x minus 2 square equal to 0. So this is the point. Take it very clearly. So what will happen once x equal to 4? Have x equal to here 2. So at this point, once x will become 4, then what will happen? Take it very clearly. X square may be 16. And x minus 2 square, it may be 4. That 4 means some this point. That means if we move further, it may be like this. See. Minus 1. Once x equal to minus 1, this kind of point, what will happen? X square equal to 1. Okay. That means this like this point will be there. 1. This point. Okay. X minus 2 square, 9. X minus 2 square, 9. Maybe this point. That means, again, this curve will be like, see the situation. What is happening? So that means, so whatever the solutions we will get from this, so that are the non-dominated solutions. It is called Pareto-optimal front. Obviously, once you are getting this solution, so this is not your non-dominated set of solutions. You may get one more solution here also, but if you implement non-domination relationship, that is not the non-dominated solution. Because all the solutions which are in the Pareto-optimal front, that is called non-dominated set of solutions. It will dominate each other solutions in the solution space. So these may be your solutions, but this non-dominated set of solutions will dominate each and every solution. But none of the solution will dominate the non-determinate set of solutions. Rather, it will dominate each and every solutions in that solution space. I hope now it is clear. Non-dominated set of solutions, Pareto-optimal set and Pareto-optimal front. So this is our Pareto-optimal front. 0 less than this, less than x, less than 2. This one is our Pareto-optimal front. Yes, what I told exactly. The same thing it is given here. This is a very known, I think, study in the concept of or context of this multi-objective optimization problem, SCAFFARD study. Again, two space is important. So as I told earlier also, you know, what is genotype, what is phenotype. Genotype means in the computational space. Phenotype means in the real life space. Real life, the problem is represented in terms of phenotype representation. And in the computational space, we will represent the chromosome in terms of what the problem, in terms of some computations or in terms of chromosomes like that. Now see, one important thing, see here, this is very much important to observe, check it very clearly. So that we SCAFFARD study we discussed, this is our Pareto-optimal front. This may be the other solutions, okay? See, proximity of two solutions in one space does not mean that proximity in the other space also. So here maybe the proximity of two solutions here, A and B, in this space, this is the phenotype space. So that may not be same to the genotype space. As I am telling, genotype means problem representation in the computational space. Phenotype means problem representations in the real life space. Real life, distance of those two solutions may be something, but once you are framing it in the computational space, the distance may be different. Spacing may be different, may not have the same proximity. Yes. So this is very much important observations to note. Yes, so a solution is said to be Pareto optimal if no solution dominates it. Repeatedly, I told you. Okay, now let's come. So if we take the minimization problem, where all the objectives we want to minimize, F1 we want to minimize, F2 we want to minimize, obviously, then this kind of Pareto optimal front we may expect. So these are our Pareto optimal set of solutions, all non-dominated set of solutions. See here, all the solutions in this front, they dominate these solutions. Similarly, if you consider this maximization problem, then your Pareto optimal front may look like this one. Maximizing, you are maximizing F1 objective as well as you are maximizing F2 objective. That means that all of the solutions here in this Pareto optimal front, they dominates the other solution. These solutions, they dominates. Maximizing, here all F1 and F2, you are maximizing. Similarly, so this is mean already we have discussed. This is max. Now, if you consider min max, then maybe this kind of Pareto optimal front you may generate. Now, if you are getting max min problem, that means F1 you are maximizing. At the same time, you are minimizing F2. Then you may expect this kind of Pareto optimal front. So these are all the bi-objective Pareto optimal solutions. Gradually, we are moving to this our NSG2. So here now quick difference between single objective and multi-objective optimization. So obviously, in the multiple conflicting objectives we will get as opposed to single objectives. Now, one important thing in the multi-objective optimizations, we need to satisfy these two goals. One is convergence, second one is the diversity. See the difference. So convergence means what? We need to progress towards the Pareto optimal front. As you can remember in the single objective optimization, we need to progress towards the best solution. Here we need to progress towards the Pareto optimal front. Okay, the solutions which will be very much closer to the Pareto optimal front, only those solutions can be selected. True Pareto optimal front is never can be obtained. True Pareto optimal front means it is the best quality solutions. As our assumptions or our considerations that none of the optimization techniques will guarantee to give you the true Pareto optimal front. Rather, they give you the solutions which are very much closer to the true Pareto optimal front. Also, you should determine that whatever the solutions are there in the Pareto optimal front, they should maintain a distance among them. That is known as diverse set of solutions in that Pareto optimal front. That I will tell you. See, this was the problem. Here there are number of solutions. So what our objective? Our objective was that, so this is a minimization problem. Our objective is that we need to move towards this Pareto optimal front. This is our true Pareto optimal front. We need to move. We should be close as possible to the true Pareto optimal front. That is called convergence. See, progressing to the true Pareto optimal front. And secondly, we should maintain the diversity. Diversity means what? Whatever the solutions you are getting, the solutions should be well diverse. The solutions should not be grouped here like that. It should maintain a well-defined distance. It should be well diverse. It should cover the whole spectrum of the Pareto optimal front. Like that, these two are objectives once you are solving for this, I think, multi-objective optimization problems. Come after 5 o'clock. Now, so this is the properties for the good solution set check. So already I told that, you know, that Pareto optimal, once we are solving multi-objective optimization problem, so convergence and diversity. So this is our true Pareto optimal front. Convergence means we are progressing towards the Pareto optimal front. And at the same time, the solution should maintain a distance among them. See here. So if you see the green colored solutions, what you will get here? This is very much closer to the true Pareto optimal front. As well as here, they are well distance. They are maintaining a good distance with each other. If you look closely to the red solutions, also this may be closer to this Pareto optimal front, but they are grouped. They are maintaining some group. Here is a group, here is a group. So this is our not well-deserved solutions. These solutions are not better. Okay, so that we should go for the solutions which are well sparsed or well distanced from each other, and simply they covers the whole spectrum of this true Pareto optimal front. Yes, now, yeah, so that was our main objective for this multi-objective optimization problem. A set of solutions should be well diverse. It should close to the Pareto optimal front. It should cover the whole spectrum of this Pareto optimal front. Now, so this multi-objective evolutionary algorithm, so we'll find out many more multi-objectives optimizations are there, starting from NSGA, non-dominated sorting genetic algorithm, NSGA2, this is an upgradation of NSGA. Right now, NSGA3 also are available. Then another algorithms are there. So today, we limit ourselves on discussing on this topic for the next half an hour, that is non-dominated sorting genetic algorithm. Now, already you know the concept and flowchart of genetic algorithm and some well-known concept of multi-objective optimization problem. I believe that will help you to understand this NSGA2 in much more better manner. You know, NSGA2 is said to be a foundation for this multi-objective optimization problem. So that means if someone is working on multi-objective optimization problem, they should know NSGA2. So then it will be very much comfortable to work more or to work further in this domain. Now you may see here using this flowchart, I am trying to convey what is the difference between single objective optimization problem, single objective GA, and multi-objective GA. So this is the flowchart for this multi-objective GA. Normally we called it MOGA, multi-objective genetic algorithm. So can you tell me what is the difference between these two flowcharts? All things you are getting almost simple, almost similar. The difference is there in environmental selection. See, if you look closely, so this environmental selection, this block was not there for single objective GA. But environmental selection, this block is here for this multi-objective GA. Yes, you are right only. If you observing this, it's very much correct. So now for the next 25 minutes, our entire focus will be to understand this environmental selection only, how to implement it. If we can understand, everything will be fine. See, what is the importance of NSGA2 that was proposed by Professor Kalyanmoy Deb and his colleagues in 2002? You know, sir now is in State Michigan University, USA. See here. So particularly this particular paper got these many citations from 2002, almost 50,000 citations. Can you believe that for a particular paper, this much citations we are getting? Sir has got this much citations. You know, citations, impact of citations. Once, when we cite some paper, once we are getting benefited from that paper, only then we are citing that particular paper in our own paper. 50,000 citations, it's not a matter of jokes. From here only you can feel the necessity or importance of this NSGA2. Fast elicit multi-objective genetic algorithm. So NSGA2, so that is our discussion topic right now for the next 25 minutes. So firstly, I will tell you the algorithm in terms of flowchart, in terms of some graphical representation. Then I will tell you the pseudocode for that. Remember, the same NSGA2 we will implement tomorrow in my next session from 3 to 5 using Python programming languages. So that means you need to understand it in detail. Okay, so that you should feel comfortable once I will implement it using Python. See here. So this time equal to 0, initial generation, P0, meaning what? Parent solution, which is of, let us say, size m. Okay, initially you are getting some parent solutions. Next, parent solution means what? Initial population. Then from this initial population, we are getting offspring solutions, that is of size m. How you will get from P0 to Q0? Implement genetic algorithm, implement natural selection, implement crossover, implement crossover mutation, you will get P0 to Q0. That means, okay, from these parent solutions, we are getting that much offspring solutions. Then, now see, this is entirely NSGA. So make a union, P0, Q0, combine these two solutions, parent as well as offsprings. You will get a solution set size at 0, which has of size 2n. See. Next, what is our objective? Our objective is that from this set of 2n solutions, we will convert into n-based solutions. From these 2n solutions, we will try to determine which are the best n solutions. How to do that? To do that, you need to implement this environmental selection. Yes, this will find the best n solutions from those 2n number of solutions. And as I said, that you need to implement convergence and diversity. To implement convergence, you should follow fast non-dominated sorting. To implement diversity, you should follow crowding distance mechanism. Let us assume our environmental selection is over. I will tell in details for the next 20 minutes. Let us assume environmental selection is over. Next, after that, what you will get? In the next generation, you will get n number of solutions. Okay, those n number of solutions belongs to PT. It is a parent solutions. Then from PT, again you will find QT. That is again n number of solutions you will get. Here you will apply genetic algorithm concept from PT to QT. Next, again we will combine this PT and QT. We will get RT. Next, yes, we will repeat this main loop. Yes, if you have got it, this is the main loop or main flowchart for this NSGA2. I hope all of you are getting. So remaining things are very much simple. Only we need to focus on this environmental selection part. Let's focus on it. Okay. So here initially we have parent solutions of size n. From that we got offspring solution of size n. That means now we are getting 2n number of solutions. You see, so on those 2n number of solutions, now our objective is we should get n number of solutions from this 2n number of solutions. How to do that? We need to implement environmental selection. Two parts. One is convergence, one is diversity. Convergence you will need to implement using fast non-dominated sorting. What is fast non-dominated sorting? So it will give you some fronts. Check it. Front 1, front 2, front 3, front 4, like that. What does it mean by the fronts? Fronts, each and every front means collection of some solutions. Front 1, some set of solutions will be there. Front 2, some set of solutions. Similarly, front 3, front 4, front 5. And here our assumption is that front 1 solutions are better than front 2. Front 2 is better than front 3, and so on. Okay. So on these all fronts, you are getting 2n number of solutions. Okay. Here we are getting 2n number of solutions. Our objective is to get n number of best solutions from all these fronts. As you know that front 1 solutions are better than front 2, so directly we will copy front 1 here. Okay. Next, as you know, front 2 is much more better than front 3. Directly copy front 2 here also. You know, front 3 is much more better than front 4. So can you directly copy front 4? Then what will happen? Size will be more than n. This is not our objective. Our objective is that we need to get n number of solutions only. Then what to do? Then some kind of sorting mechanism you need to do on this solution set which is on front 3. That means if you sort the elements or solutions in front free and simply copy and simply see, yeah. So and simply copy the best solutions from front tree, and remaining solutions you can discard. Once again, I will make it clear. Check. From front tree, entire set of solutions we cannot copy here. So front tree, we are implementing some kind of sorting on this front tree solution set. And which are the best? Only those solutions we are copying into here. Remaining solutions, so these much solutions we are copying here, and this remaining solutions simply we are discarding, we are rejecting it. So this is the conceptual idea behind it. Now let us see how to implement fast non-dominated sorting and the crowding distance. See here, this is our fast non-dominated sorting. So these are solutions. Suppose that we are getting solutions PT, that means the parent solutions. Okay, from these parent solutions we are getting the offspring solutions, that is QT. Now, so for the sake of simplicity, we are numbering the solutions. See, we are numbering all these solutions, and what you are computing, RT. RT means what? It is PT and QT. Collection of PT and QT, it will give you RT. So total solution is 8, 4 plus 4. Your objective is you need to select the best 4 from this set of 8 solutions. How to do it? That is the fast non-dominated sort. Let us start with that. Yes. What is the idea? For each and every solution, so remember, this is a minimization problem. For each and every solution, you need to determine that solution 1, how many which solutions it is dominating. Solution 1 dominates 5, 4, 8, 7, 3. If you can remember the idea of dominance, you will get it. These are minimization problem. So 5, 4, 8, 7, 3, these are dominated by solution 1. So keep it in this domination list. How many solutions dominates 1? None of the solutions dominating solution 1. This is called domination count, N1 equal to 0. Do the same thing for each and every solutions. Now for solution 2, check it. For solution 2, 7 and 3 are dominated by solution 2. So keep it in the list. How many solution dominates 2? None of the solution dominates 2. Make it 0. So you need to follow these steps for each and every solution. Check it. For solution 3, what is happening? None of the solutions are dominated by solution 3, but 3 solutions, 1, 6, and 2, dominates solution 3. So that's why it is empty, and this is count is 3. Since it is 1, 2, and 3. So this similar thing will implement for each and every solution. See, try to get it. So we'll get these, all these sets as well as all these counts, non-domination counts. Now identify for which solution count is 0. So for this 1, this, and this count is 0. 1, 2, and 6. That means your 1, 2, and 6 will build up the fast non-dominated front. Try to get it. How we are computing the fronts? So it will give you the fast non-dominated fronts. Next, what to do? For each and every solutions in the fast non-dominated front, try to find which are dominated by these solutions. That means which are dominated by solution 1. Which are dominated by solution 1? These many solutions are dominated by solution 1. Reduce their domination count by 1. Check. 5. Reducing domination count by 1. 4. Reducing domination count by 1. 7 by 1. 8 by 1. 3 by 1. Do the same steps for each and every solutions which are on this front one. For solution 6, do the same process. Which solutions are dominated by solution 6? Reduce their domination count by 1. 8, 4, 7, 3. This 4, 8, 7, 3. Reducing again their domination count by 1. Check it very clearly. Check it very clearly. So once again, I will make it simple. Check it very clearly. Again, to implement the same thing for solution 2, do the same thing. Which solution it dominates? 7, 3. Reduce that domination count by 1. Check it. 3. Reducing by 1, 7. Reducing by 1. And now find out for which solutions this domination count is 0 and put them in the second non-dominated front. Yes, if you find, so this, that means 5, 8, and 3. Check this 3, this 5, this 8, and this 5. This count is 0. Now these are under our second non-dominated front, second front. Similarly, you need to calculate the all other fronts and we will get our third front. Take it here. This is called first non-dominated sort. This is entirely graphical representation. Today I will show you the pseudocode and total implementation of the pseudocode I will show you in my tomorrow's session. I hope that you are getting, for using the first non-dominated sort, simply you are dividing those elements into some fronts, some set of fronts. And obviously that set of solution in the front 1 better than front 2. Set of elements in the front 2 much more better than front 3, like that. So this is the first non-dominated sort pseudocode, whatever right now I have explained. Okay, so that entire pseudocode tomorrow we'll implement using Python programming. So exactly what I told, the same thing is there in the pseudocode. So today I will not come to the pseudocode, it is our job of tomorrow. So whatever I told using graphical presentation, entirely the same thing we will find out in the pseudocode. I will not go through it. Tomorrow we'll see it. So our first non-dominated sorting is over. Next, what is our task? Our task is to go for the crowding distance. As you can remember, why to go for the crowding distance? You can check it here. Why to go for the crowding distance? Check it. Yes, so we have seen that in this particular front, if we consider all those elements, then total capacity may be more than n. But it should be n only. That means from front 3, we should select some solutions which are much more better. So we need to rank the solutions in front 3. So how to do that? To rank the solutions in some front, we need to know this crowding distance mechanism. Let us see. Yeah, so this is that. Now we'll go for the crowding distance mechanism. Crowding distance. So let us see. So suppose these elements are in some front. Among these elements, we need to select which is better one. See how to do that. So denote half of the perimeters of the enclosing cuboid with this nearest neighbor solutions, the same front. With this solution, these two are the nearest one. So find out the perimeter and half of the perimeter you compute. That will give you the crowding distance for these solutions. That means crowding distance will be more if those are well diverged. Crowding distance will be less if those are very closely related or very I think distance is very less among them. And here we assume that all the extreme 2 elements crowding distance is infinite. Our target is we should avoid the crowd. Yes, if we can avoid the crowd, only then we can say the solutions are well distant along to the, I think, that Pareto optimal spectrum or Pareto optimal front. Yes. So now I hope that you are getting that the non-dominated sorting as well as the crowding distance. Now how to do the rank. So firstly, we will do the rank based on that non-dominated sorting. As you know, front 1 elements. So these are much more quality solutions rather than front 2. So front 1, front 2, front 3. So these are descending orders. Front 3 much more high quality than front 2. Front 2 rather than high quality than front 3, like that. Yeah. Now, obviously, so if we need to compare among the set of solutions, assuming every solution have a non-dominance rank as well as crowding distance C, a solution I wins the tournament, that means better, with another solution J when if the solution I has a better rank. Obviously, if rank of some solution is more, that means rank of the front. If it is more, front 0 is much more better than front 2 is better than front 3, like that. So if the solution rank is more, it will be good solution. If rank is same for those two solutions, then we need to go for the crowding distance. Okay. Yes. The same rank, but I has better crowding distance than solution J, then obviously I is better than that of J. So these are the crowding distance. Again, tomorrow we'll see how to determine this crowding distance. So based on the objective functions. And now almost we are closing the fact. So these are the main loop for our NSGA2. So you can remember. So initially we computed the combination collection of this parent solution and offspring solutions. Then we went for non-dominated sorting. So these are the part of environmental selection. Non-dominated sorting, first non-dominated sort. Then what we did, you can remember. Then after the first non-dominated sort, then so what we are doing, so here pt plus 1 equal to 9, ln I equal to 1, that means we are moving to the next iteration. So here we are finding the crowding distance of all the elements in the ith front. Then we are from the ith front we are attaching to pt plus 1. We know that pt plus 1 ultimately the size should be n. So we should include the elements from the fronts in pt plus 1 in such a manner size of pt plus should be n. For that purpose only, you need to do the crowding distance. Okay, I equal to I plus 1, check it. So while, so that means elements from the ith front will include in pt plus 1 until unless that is less than equal to n. Suppose right now in pt plus 1, okay, there is 10 solutions, suppose. And your n mean, value of n means 15. What are the remaining solutions? 5. So these remaining 5 solutions, where you will get? You will get from next front. Suppose in your next front, number of solutions are 20. Then from this 20, you need to find out this best 5 using the crowding distance mechanism. That's why it is written. Next front, you need to sort. Okay. So after sorting, see this n minus pt plus 1. Pt plus 1, what is the value? N, what is n here equal to 15. Pt plus 1 equal to 10. That means you need here 5 solutions. From this front type, you will include 5 solutions to this pt plus 1. So that it will become n, which is what is in our example, that is for 15 right now. Okay, so once it is done, then what you will do? Then you will go for generating the offsprings qt plus 1 from this pt plus 1. Yes, then you generate the offspring from qt plus 1 as you have seen in our main flowchart. So this is again the pseudocode we can say for this non-dominated sorted genetic algorithm. The entire thing, as I was explaining, that I will implement tomorrow using this Python coding. So today try to understand the concept behind it so that tomorrow will feel easier, feel comfortable. Now this is the flowchart of this NSGA2. So see the flowchart of this NSGA2. Again, I have repeated it. So mainly we have implemented the environmental selection, you can remember. We have implemented first non-dominated sort, got some set of fronts, okay, that is required for convergence. And also for maintaining diversity, we have explored the crowding distance mechanism. Mainly once some set of solutions are in a particular front, to make a order among them, we need this crowding distance. Now this is our NSGA2 main loop. Again, what I told right now, so that this is another pseudo code. So RT, we need to combination of this parent parent and offsprings, first non-dominated sort. We need to include until unless the size is less than equal to n. Remaining things we need to take from the next front, but from the next front we will not consider all the elements. Based on the crowding distance only we'll consider. And then once PT plus 1 is formed, we'll go for forming QT plus 1. So this is the pseudocode for this NSGA2. And again, step-by-step manner, here I have written that what I was doing in various steps. Step 1, so this is, then next it is step 2. So this is written in a stepwise manner to make it much more easier. So this is now a summary of everything, non-dominated sorting GA. So it was PT, QT, so size PT, it was size n, QT size n, this entire thing size 2n. Then using non-dominated sorting F1, F2, F3, so this will give you collection of 2n number of elements. If you will get summation of all these fronts elements, it will give you 2n. So from this 2n, in PT plus 1, we need exactly n. How to do that? As front 1 elements are better than front 2, directly we'll copy front 1 as we have discussed earlier. Front 2 may be better than front 3, so directly we'll copy front 2. But what will happen if we copy entire elements from front 3? Size will be more than n. It will not be fitting here. What to do? So from the front 3 elements, we'll go for crowding distance. Crowding distance means it will give us a ordering of the elements in front 3. So based on the ordering, whatever the required elements to fit, to make it into n, so that much elements only, solutions only, will take from front 3. And remaining solutions will discard. Entire thing is carried out by this crowding distance mechanism. So in brief, or in a summary, so this is our non-dominated sorting genetic algorithm. Yes, now main advantage for this non-dominated sorting GA, so see, a diversity among the non-dominated solutions is maintained using the crowding distance procedure. See that. No extra diversity control parameter is required. As you know, maintaining diversity is very much important. As you have seen that once we are discussing the single objective genetic algorithm, then I told you that the mutation part that will help us to explore the search space extremely. Like that, you need to use crowding distance mechanism to maintain the diversity. Otherwise, some solution will be grouped together and your entire search space may not be visited or may not be explored. And one thing important, as we have seen the elitism mechanism that protects the already found Pareto-optimal solutions from being deleted. Take it very clearly. So elitism, that means the most powerful solutions, most better solutions, I think high fitness value solutions, obviously you need to protect it. No, don't need to apply crossover mutations, any other operations on these highest category kind of solutions. So yeah, so that will give you a quick convergence. Simply you can say that protects already obtained Pareto-optimal solutions from being deleted. So that is all about regarding this, our multi-objective optimization. So my acknowledgement to Dr. Professor Chandrapal, Department of Computer Science and Engineering, NIT Durgapur, for providing me that graphical presentations and giving me the concept so that I can tell to my participants in quite comfortable manner. Now these are the reference, all papers from Kalyan Moydev only. So Professor Kalyan Moydev, normally we see the father of this multi-objective optimization techniques. As I have seen, as I have shown you, that the paper NSGA2, what sir has, I think, published in 2002. So far the paper already got 50,000 citations. Now all those who are working in this domain, multi-objective optimization, normally consider that paper as our base paper. So it is necessary to understand that paper. If you can understand that one, today whatever the concept I discussed, all concept belongs to the paper only. So if you have understood it, then it will be very much helpful for you to understand the NSGA concept or multi-objective optimization concept. So that's all about from my side. So it's almost 5. So thank you. Now, if you have any quick queries, I'm ready to take some queries. Also, participants, please note that I have given my email ID as well as contact number. This contact number is also my WhatsApp number. So feel free to message me or to communicate me through my email ID. If you have any queries right now, feel free to ask. If you have some queries in future, recent future also, so feel free to communicate me. So I'll be ready to answer. So waiting for some queries. If you have any queries, please ask. Also, you can type in chat box. So let me check the chat box if there is any query. So no, I did not find any query in the chat box. Anyway, so since tomorrow again I will be here on these sessions, I think same sessions from 3 to 5. So if you have some queries, so you can write down your queries in your notebook. So tomorrow at the beginning of the sessions also, you should feel free to raise your queries. Definitely, I will try to solve all those queries. So that's all from my side. Now, once again, I want to thank to the participants for their patience to listen me on the last 2 hours. Over to Madam.
Thank you, sir. Thank you, sir.
Okay. So thanks to the once again, thanks to the coordinators of this FDP and to invite me or to give me the opportunity to share my thoughts here. So thank you on and on.
Thank you, sir. So we'll start the next session after 5 minutes.
Sir, good evening, Saras sir. Sir, good evening, sir.
Good evening, Dr. Sanjay Kumar Konda. And
Shall we start, sir?
Good evening, sir. Good evening.
good evening, Manjuvala madam, and good evening to all participants for this session.
Sir, just a minute, sir. We'll start. I'll introduce you.
Yeah.
So I welcome all the participants to the second session of day 7 and in day 8. So in this session, Dr. Saras Chandra Naik sir is with us. So he'll discuss about artificial electric field algorithm, and maybe in the next session he will discuss about higher order neural network, chemical reaction optimization. So before Dr. Saras Chandra Naik sir will start the session, let me introduce him. So Dr. Naik holds a PhD degree in computer science and engineering from BSSUT Bulla in the year of 2016. His research interests are machine learning, data mining, soft computing, predictive system, financial time series forecasting, computational intelligence, and evolutionary computation. He has more than 80 research articles in various reputed international journals as well as conferences, and one book and 13 book chapters in his credit. He has more than 16 years of experience in the field of teaching and research. Currently, he is associated with Soft Computing Lab at Wonsai University, Seoul, South Korea, under the supervision of Professor Sangbon Chow as a postdoctoral fellow. So, with this introduction, I request Dr. Sarat Chandra Naik sir to start the session.
Okay, sir. Thank you, Dr. Konda. So let me share my presentation. Just 1 minute, and a small request from my side. For a short period of time, I am staying in India now, and right now I am using my mobile data. So my mobile data may not be sufficient. If some technical problem will be there, I may switch over to another mobile. So please cooperate me in such interruptions. And just a minute, let me share. Is my screen visible to everyone?
Yes, sir.
Okay, thank you, sir. Okay. Good evening once again, all the participants and NIT Warangal Department of Computer Science. And my special thanks to Dr. Manjuvala Bishi ma'am and Dr. Sanjay Kumar Konda for giving me such opportunity to share my knowledge with all the participants. And as the theme of the FDP optimization, so here I'm going to share my knowledge, my experience on meta-heuristic optimization of higher order neural networks for financial time series forecasting application. So, as Dr. Ponda told everyone that I have been working on this area from last 10 to 12 years, and I have few works on this meta-heuristic optimization of artificial neural network as well as higher order neural networks. and I applied my hybrid models or my optimization techniques on financial time series forecasting as well as other optimization techniques and other engineering applications. So today, my presentation outlines will be, I will give you a small introduction about higher order neural network. Then I will explain you one of the interesting optimization technique or evolutionary optimization algorithm, that is your chemical reaction optimization. Then tomorrow session, I will explain you another optimization technique that is called artificial electric field algorithm. And today as well as tomorrow, I'm going to give you a small demonstration about my applications on financial time series forecasting. And here I declare that some of the materials are collected, used in these presentations are collected from available literatures as well as internet sources. So let me very quick give you a small introduction about artificial neural networks. I hope nowadays each and everyone know about artificial neural networks and worked on artificial neural network. I hope almost all the universities they included an artificial neural network or simply neural network as a course for BTech as well as AI and ML. So, a neural network is a machine learning approach inspired by the way in which the brain performs a particular learning task. Okay, so it is mimicking, it is simulating the human brain, right? So, what are the learning tasks? Knowledge about the learning task is given in the form of examples. We are a human being. Every day or every time we have been learning from different examples, right? Like student, we practice different type of examples, and from those examples we learn something, we acquire knowledge, and we are applying that knowledge to solve other type of problems, right? Interneuron connection strength, I will show you few diagrams about neural network. Interneuron connection strength, or those are called weights and biases, are used to store the acquired information. The information extracted from the examples are stored in the form of weights associated with the connected associated with the just a minute, just there is some interruption, please. Sorry for interruption. So, and during the learning process, you might have heard about the term machine learning and the particular term learning, right? So during the learning process, the weights are modified. We can increment the weight or decrement the weight in order to model the particular learning task correctly on the training examples. So basically, artificial neural network is nothing but it is a simulated software which mimics the human brains and follows the way how the human brain learns from examples and apply the knowledge for solving similar tasks. And this is one typical example of a multi-layer artificial neural network, or simply it is called MLP, right? On the right side, you can see this is one example of a multi-layer perceptron or a neural network with multiple hidden layers. The first layer receives the inputs, let the inputs are I1, I2, or IN, right? So this is called input layer. Similarly, the last layer produces outputs of the network. Let the outputs of the networks are O1, O2 up to OM. So there are a M number of neurons. This is called output layer, and all the layers in between the input and output or layer are called hidden layers, right? So it is a fully connected network, right? The arrow mark indicates that the information flows from left to right, starting from the input layer up to the output layer, right? And each circle is nothing called one neuron, or you can say that it is simply a perceptron, and the perceptron is shown on the left corner. Hello?
Hello. Sir, sorry for interrupting. This is Mustafa Shamim
Yes,
Firdaus.
yes.
I'm a governance scholar. My humble request is that, sir, what is the basic difference between, deep learning and simple, artificial neural network? Deep neural network and artificial neural network.
Yeah. Okay. You might assume that this diagram shown on the right side of the slide, it can be considered as deep learning also. If the number of layers will be very large, then we can say that the learning process is a deep learning process, right? If the number of hidden layers is 1, 2, or 3, small number of hidden layers will be there, then we can say that it is a shallow learning or simply artificial neural network. Okay, so let's consider one neuron or one perceptron, and the diagram of the perceptron is shown on the left hand side. So here it receives the inputs x1, x2, x3 up to xr, and this is summation line. This is summation line is nothing but the weighted sum. It stores the weighted sum. That means you can see there is a arrow mark from x1 to this is summation box. So it indicates the information flow, and each arrow has one associated weight, let wi, right? And the first associated weight is called wi1, next one is wi2, wi3 up to wir. So at this is summation unit, the weighted sum, multiplication of input x1 and the associated weight wi1 will be calculated, and similarly all input multiplied with the associated weight will be calculated, and finally it is summed up, right? And one bias will be there. I'm not going to discuss what is the significance of the bias, but I request everyone, please assume that this unit calculates the weighted sum plus bias, and we may apply one activation functions that is ai. Then you can find the output yi. The equation is written on the bottom of the slide. That means w1 x1, w2 x2 up to wn xn, right? And w0 stands for bias. It is a constant. So this is the overall architecture of a multi-layer perceptron and calculation. Then where possible applications of artificial neural network? It can be applied for different function approximation or function optimization, and a lot of applications in data mining are there which are using artificial neural network classification, right? And this is another typical diagram of multi-layer perceptron. Let the inputs are x1, x2 up to xn, and the hidden layer. So this is a multi-layer perceptron. Is that only one hidden layer? I'm getting noise. I request participants please mute yourself. So it has one hidden layer, one out, right? So you can see each arrow mark is connecting one unit to another in a forward direction, and is associated with some weight range W01, W02, W05, right? And as I told,
there is a background noise. It's difficult to follow you, sir.
I think it is it from my side?
Don't know, sir, actually.
Hello?
Apart from you, some others mics are also. Yes, sir. Apart from you, some others mics are also on. That's maybe the reason.
Okay. Thank you. So The hidden layer neurons calculated the weighted sum followed by one activation function, and V0, V1, and V2 up to Vm, these are the weight values associated with the neurons rings from hidden layer to output layer. Then finally, the network produces one output that is called Y estimated. The model estimates output, and the actual output would be Y. The difference is calculated, and it's called as error signal. Minimum the error, better is the model learning, right? So, and this error signal is propagated to the hidden layer as well as input layers to update the weight and bias values. The weight and bias values are updated with the or based on gradient descent rule, and since the weight is the error is propagated from output to input layers, so it is called back propagation method. So overall, we can say that the learning process of a multi-layer perceptron or MLP is gradient descent back propagation learning, right? Because the error signals or the difference between model estimation and the actual output is propagated to the input layers or back propagated, right? So I think you are getting few noise from my side. Let me close my windows. Okay, so I hope everyone understand the working principle of a multi-layer perceptron. So it is very simple. The weight is supplied to the network at the input layer, and the weight is propagated in the forward direction. Finally, the signal is calculated. The error signal is back propagated to update the weight and the bias. So it is called gradient descent based back propagation neural network learning, right? So in conventional neural network, we can assume the learning process, we can visualize the network as a black box, because once again, I want to come to the return back to the first diagram I have shown to you, MLP. You can see there are n number of hidden layers. Okay, so if the number of hidden layers will increase, the complexity will also increase, and we cannot. It is not easy to know which neuron computes what output. So we can assume the learning process as a black box process. Okay, and since the number of layers are very large, so it leads to longer convergence time. If the computation will be more, then the convergence time will be also more, and it often stuck in local minima. So I'm not going to discuss about the local minima problem, but it is very common in artificial neural network. These are the common drawbacks, limitations of your conventional back propagation learning, right? So how to avoid these limitations? We can avoid these limitations in two ways: using higher order terms of input, and in the latter part, in the second part of this presentation, I'm going to use optimization algorithm, that is CRO. So I will explain you how you can replace, how you can overcome the limitations of propagation learning by using the evolutionary optimization algorithm. So before going to that, let us discuss about higher order neural network. It is simply an artificial neural network, but instead of using the input directly, it uses the combination of inputs, higher order of inputs. Okay, so it is a network that utilizes higher combinations of inputs, and these models are capable of simulating higher frequency and higher order non-linear data. So I know that real life data is highly non-linear. So conventional artificial neural network may not optimize or may not capture the non-linearity associated with the real data. So in that case, higher order neural network will be a better solution. And a higher order neural network expand the capabilities of a standard feed forward neural network, as I told, by including input nodes that provide the network a more complete understanding of the input patterns and their relations. Okay. And HONA or higher order neural network needs only one layer of trainable weights. Before that, let me tell you trainable weights. So let me go back to the previous diagram. Yeah, let us come to this diagram. So here only one hidden layer are there, and the total number of layers in the neural network is 3: input layer, one hidden layer, and one output layer. And there are 2 layers of trainable weights. First, the weights between input and hidden layer, they are represented as W01, W02 up to WNM. So there are n number of inputs and m number of hidden neurons. So the total number of weights will be n cross m. So it is a matrix which size is n cross m. So it is one level trainable weight. And another level of weights are there between the hidden layer and the output layer, represented as V0, V1, V2 up to Vn. Right? So 2 layers of trainable weights are there. And if n number of hidden layers will be there, then n minus 1 number of, n plus 1 number of trainable weights will be there. Okay. So a higher order neural networks needs only one layer of trainable weights. Means we need to update only one layer of weights and biases. And since there is no hidden layer or absence of hidden layer is there, so it has simple architecture and complexity is very less. And consequently, they can learn faster. They have stronger approximation property as well as a faster convergence. And popular higher order neural networks are functional link artificial neural network, or simply it is called, in short form it is called PLAN. You can find numerous applications of a PLAN in data mining tasks. Another popular higher order neural network is your pi sigma neural network, or PSNN, joint PSNN, polynomial neural network, rich polynomial neural network, then radial basis functional neural network, and you can also include random vector functional neural network, or VFLN, that is also coming under higher order neural network. So in today's presentation, I will explain you only one higher order neural network, that is called your PLAN. So PLAN has a simplified single layer architecture. As I told you, since it belongs to higher order neural network category, so there is no hidden layer. It has a flat network, but it uses functional expansion units, FE. Right? I will show you the diagram. So if a given input is X, then you apply one functional expansion process on this X to expand the inputs and to find the higher combination of inputs. Right? And these functional expansion units removes, or the use of these functional expansion units avoids the use of a hidden layer. That means in place of hidden layers, we can use functional expansion units, right, to get the similar results. So since there are absence of hidden layers, then complexity of network will be very low and convergence rate will be very fast. Okay. In conventional neural network, the computation consists of a calculation of a weighted sum of inputs followed by a nonlinear activation. So the nonlinearity is carried out only by the activation function. But here, nonlinearity is carried out by both activation function as well as higher order terms formed from the inputs. So let me skip this. Yeah, come to this diagram. This is a basic plan architecture. On the left hand side, you can see the inputs, let x1, x2 up to xp. These are the p number of inputs. Let us consider only one input, the first input x1. The input is supplied to the functional expansion unit AP, right? The functional expansion unit expands the given input x1 into different terms, different higher order terms, right? Then these higher order terms are used as the input to the neuron. It is a single neuron model. You can see only one summation symbol is there. Only one neuron is there. That's why it is a flat network. And the link between this expanded unit and this summation unit are associated with weights. So it has only one layer of trainable weights. And similar to your conventional artificial neural network, activation function is applied and the network estimates or model estimations will be computed. It will be compared to the actual input. The difference will be calculated and the difference is propagated back to update the weight. Right? So now the question is, what is the role of that functional expansion block or functional expansion unit, and what are the different functions can be used in this functional expansion unit? Right? The very basic or very common functional expansions are trigonometric functions. If one input will be xi, then different trigonometric functions like sine, cos can be applied to generate a different outputs. So those are called expanded outputs. If one input will be xi, then we may calculate a sine of xi, cos of xi, sine pi xi, cos pi xi, sine 2 pi xi, cos pi 2 xi, like this. And the number of such functions is your part of experimental work. You have to try with different functions with different number of functions also. Then another popular functional expansion unit, functional expansion process is your Chebyshev polynomial. You can generate a different polynomials using this formula and your original input xi. Another functional expansion can be applied by using Laguerre polynomial and Legendre polynomials. Apart from these, other polynomials might be there. Particularly in my research work, I applied these 4 types of polynomials or functions in the functional expansion block. So let us see this diagram. This is a functional linked artificial neural network which uses different trigonometric functions in the functional expansion block, right? So you can term this network as a trigonometric plan, right? So please have a look for a few seconds. Please have a look on the diagram. The inputs are x1, x2 up to xn, and all the inputs are passed through functional unit block, and a different higher order terms are generated along with the original input x1, sine pi x1, cos pi x1, like this, right? And the associated weights are there represented in the terms of w, w11, w12, like this. And as I told you, there is a single neuron, only one layer of a neuron. So at neuron, the weighted sum is calculated, and activation function, let the activation function is tan h, right? And the error is back propagated. So this is one typical diagram of trigonometric functional link artificial neural network. Okay. Then let us see the computation, how it computes the output. Let the original input represented by xt. At a tth time, the input is capital X, I mean, it includes the inputs x1, x2 up to xd. This input is passed through functional expansion unit. Let the expanded input set is x dash. Right? On the left hand side, the original input xt. On the right hand side, after applying functional expansion process, we can get or we can generate the expanded input x dash. Right? And the original input is d-dimensional input vector, whereas the expanded unit or the expanded input vector each consists of more number of dimensions. Let the weight associated with the network is WT. So given the expanded input x dash, using weight WT and bias B, the model produces an output y dash t. So how it is calculated? Y dash t equal to expanded weight set x dash into associated weight WT plus bias, and T stands for transpose. Capital T stands for transpose, right? And then the output, model output or the network output is passed through one sigmoid activation function or a tan-H activation function, any activation function you use, and the output is y cap t. Then this output y cap t is compared with the original or the actual or the true output yt, and the error signal et is calculated. So this is the computation in plan, right? If you have any doubt, you can raise a question now also. At any time, you can put a break on me, right? The error signal is calculated, and as I told you, the error is propagated to update the weight and bias. The weight and bias are updated using this formula. So I am not going to the complete derivation of this formula. Only you can follow different articles or you can follow different books to find how the weight and bias are updated. Just like a simple neural network plan, in case of a plan also the weight and the bias are updated like gradient descent rule. Okay, so this is another neural network called pi sigma neural network. It applies pi and sigma, both, I mean the summation process as well as the multiplication process. So let us skip this. Then let us go to discuss a interesting meta-heuristic optimization algorithm that is called your chemical reaction optimization algorithm. So before going to optimization algorithm, I request you, if you have any question on functional link artificial neural network, you can raise it now. Otherwise, I may proceed. Okay, if I have no questions, so let me go forward. I'm not going to repeat the definition of a meta-heuristic because from last few days you have been learning about optimization algorithm, or simply they are called meta-heuristics. So let me skip this. Directly I am coming to chemical reaction optimization, and henceforth I will use the term CRO. Okay, so before that, let us discuss about what is the meaning of a chemical reaction. In chemistry, all of us studied chemical reactions. So am I audible to everyone? Can I get response? Am I audible to everyone?
Yes, sir. Audible.
Okay, thank you, ma'am. So a chemical reaction is a process that leads to the transformation of one set of chemical substances to another. So this is a very common definition about chemical reaction optimization. Chemical reaction. Forget about the term optimization. we are discussing about chemical reaction. So it is a process that leads to the transformation or change of one set of chemical substances to another. And the substances initially involved in a chemical reaction are called reactants. So there are two terms called reactants and products. So the initial chemicals which are involved in the reaction are called reactants. So different reactants interact with each other to produce different products. Chemical reactions are characterized by chemical changes. One or more products which usually have a properties different from the reactants are produced. The properties of a product are obviously different from the properties of reactants, right? And the reaction process continues till the equilibrium point is achieved. I mean, the reactants are become inert, or that is called equilibrium state. Or you can say that the rate of a forward reaction is equal to rate of a backward reaction or a reverse reaction. At that point, the process will stop, right? So please have a look on this diagram. Different types of chemical reactions. Actually, I'm not discussing exactly what is the chemical reactions in the term of chemistry. Rather, I want to show some pictorial view of a chemical reactions. Suppose two reactants join with each other to produce a new product. The first line diagram. This is called combining to make new one. Right? Two reactants with different properties combines with each other, produce another product of a different characteristics or different properties. Right? The second one is changing combinations. If we change the combination from a set of reactants, we can find set of products. Right? Or you can go through decomposition, breaking apart. Let us start from one reactant and decompose it, get a different product. Right? So this is the overall picture diagram of different types of chemical reactions. So the chemical reaction involves combination, changing, or decomposition. Right? Now, this is one example of a synthesis reaction. Hydrogen reacts with the oxygen, gives water. It is called a synthesis reaction. Right? Two reactants, hydrogen and oxygen, combine with each other to produce water. And its opposite is decomposition reaction. When water breaks or decomposes, it gives hydrogen and oxygen. Okay. Similarly, you can find it different types of chemical reactions. Single displacement reaction, double displacement reaction, reversible reaction. Okay. So please don't assume that I'm teaching you chemistry, but before explaining you chemical reaction optimization, I want to remind you different types of chemical reaction and what are different types of chemical reactions are there. Right? So this is the basic concept of chemical reactions, not optimization, chemical reactions. Atoms and molecules move and collide. Please underline the word move and collide in a continuous manner in a viscous fluid filling or 2D cellular space. Assume that one vessel is there, and inside that vessel some chemicals are there of different characteristics, different properties. Right? So they collide with each other, or they move from each other in a continuous manner. Right? We can assume the atoms are the elementary particles. Right? These are the elementary particle of a chemical reaction, atoms, and they possess type, mass, radius, charge, orientation, position, and velocity. Right? Atoms are called as elementary particles of a chemical substance which possess these type of properties: mass, type, radius, charge, orientation, position, and velocity. A molecule is a set of atoms connected by bonds. Right? Chemical reactions are mappings of discrete cellular configurations to parameterize actions on atoms. And the actions from creation and destruction. Atoms can be created in this, in terms of optimization algorithm, atoms can be created and destroyed. Right? Then come to algorithm. Algorithm can be considered as a simulation of reactants in a vessel. Right? Different reactants are kept in a vessel. They react to each other to formulate or to form a final product. Right? Similarly, algorithm takes different inputs, apply different search operations, and find a final output. Right? So let Ri be the list of a chemical species, and suppose these species can interact through M specified chemical reaction channels. Let one vessel contains Ri number of chemical species or chemical substances, and M number of chemical reactions are applied on Ri. What can be the different type of chemical reactions? As I shown you earlier: synthesis reaction, decomposition reaction, displacement reaction, like this, redox reaction. Like this, M specific chemical reactions are applied on Ri. Ri is nothing but a list of chemical species contained in a vessel. Reaction rules define the interaction among one or two reactions which may lead to products to, actually it is a spelling mistake, may lead to production of a new reactant. Okay, so let us come to our conventional or common optimization algorithm process. So you might have studied different different optimization algorithms, like different resource persons, they have explained about optimization algorithms, like a particle form optimization, TLBO, and a genetic algorithm. Right? So in every optimization algorithm process, we start from initialization. Right? We start from initialization. Let us start from some random solutions, and while stopping criteria is not matching, keep on applying different search operators. In case of a genetic algorithm, what are the different search operations? Your crossover, mutation, and selection. Okay. In case of your particle swarm optimization, we are applying how to update the position and how to update the velocity. Right? And we are keep on applying these search operators till stopping criteria. Right? Then increment the iteration and repeat. And finally, the algorithm will return us the best solution. This is your conventional optimization algorithm process. So let us formulate chemical reaction optimization process, or CRO. It begins with a set of initial reactants in a solution. So this process is similar to your initialization step. Then apply different type of chemical reactions on these reactants to consume and produce different products. So these different type of chemical reactions can be assumed as the search operations, right? And these search operations will continually applied on the reactants till the termination condition. The algorithm is terminated when the termination criteria is met. Either you can consider the number of iterations, or you can consider the smallest threshold, the smallest or the threshold value of your error signal. Okay, so if you summarize, the major step of your chemical reaction optimization will be problem and algorithm specific parameter initialization. And please note that in case of chemical reaction optimization, it requires no algorithm specific parameters. For example, if you consider your particle swarm optimization algorithm, so few algorithm specific parameters are there. If you consider your genetic algorithms, then few algorithm specific parameters are there. Those are your crossover probability, mutation probability, right? So in order to find the best result, have to fine tune these algorithm specific parameters, or those are called control parameters. But in case of a chemical reaction optimization, there is no control parameter, or there is no algorithm specific parameters, right? It is straightforward optimization algorithm which does not require any algorithm specific which does not require any algorithm specific parameters. Only you need to specify the number of reactants. It is similar to your number of individuals. Okay, then the step one is problem and algorithm parameter initialization, setting the initial reactants, then and evaluate, apply different type of chemical reactions, update the reactants, and check the termination and stop. Okay, so these are the major steps of your CRO, chemical reaction optimization. So up to this, if you have any question, please raise your hand. Let me repeat. Chemical reaction optimization simulates the process of natural chemical reaction operations. Natural chemical reactions starts with a set of chemicals, those are called reactants, and followed some specific number of chemical reactions, and finally stops when the reaction or when the liquid becomes inert, right? Okay, so let me go to the next slide. So let us see the chemical reaction optimization process in the form of a flow chart. Actually, this is my implementation. So you can find different versions of a chemical reaction in the literature, but exactly this flow chart I use in my implementations, right? So there might be plus or minus when compared to your basic CRO. So the process starts with initialization of reactants, or the process is called reactant initialization. Then check whether to apply intermolecular reaction or collision or intramolecular collision. For example, if one molecule will be chosen, then it is called intermolecular. Otherwise, it is called intramolecular, or more than one molecule will participate in the reaction, right? So if intermolecular collision condition satisfied, then let us check whether it is satisfying decomposition condition or not. If it will satisfy decomposition condition, then we will apply decomposition reaction. Otherwise, we will apply a redox reaction. right? And these probability value, for example, in this condition satisfying intermolecular collision condition or not, I used a random value of 0.5. So this value is specific to my applications. It is not a standard value. You can experiment with different values as for your problem. Okay, so please for a few seconds, please have a look on this flowchart, and if you have any question, please raise it now. Can we have a short break on now? If Dr. Sanjay Kumar Panda or Manjuwala BC ma'am is there, so I may request let us have a 5-minute break.
Okay, sir.
Or if you are not interested for a break, let us continue.
Sir, actually, it's your
Okay.
take. If you want
But before that, please
I
have
mean,
a
want
look
to
on
give
this
us a break,
flowchart.
then okay.
Okay. Let us continue for a few minutes. After 5 minutes, I will have a short break. Okay. So let us come to the next slide. Then, like other optimization algorithm, chemical reaction optimization algorithm also follows encoding process. Right? Encoding process means in what form you have to represent your individual. Right? So as I told you, in case of a CRO, the individual is nothing but a molecule. Then how to represent that molecule? Right? So two types of encoding methods are there for CRO. One is binary encoding, another is real encoding. And in most of my applications, I used binary encoding. So I don't have experience with real encoding. Binary encoding means to represent the encoding process in the form of a 0 or 1. Okay, so please look at the slide. Suppose there is a single molecule M, and it is represented by 0, 1, 1, 0, 1. It is nothing but a binary string. One molecule can be represented with the help of a binary string. So let this molecule decomposes into two parts, M1 dash and M2 dash. And let the binary encoding for M1 dash and M2 dash is represented by 11101 and 0100. So this is an example. Okay, so in this way you can represent a decomposition reaction, decomposition of a single molecule M into two molecules M1 dash and M2 dash. And how to represent a redox reaction? Let us start with one initial molecule M with values 1, 0, 1, 1, 0. And you just flip few bits of original molecule M to get a new molecule M dash. Actually, there is no specific rule how to represent reduction reactions or how to represent different chemical reactions in CRO. Right? So, in my applications, I use this type of encoding process. Similarly, let us go with a synthesis reaction. Synthesis reaction means two molecules combine with each other to form a single molecule, another single molecule. Okay, so let the one molecule is there M1 plus another molecule is there M2. They combine with each other, followed by synthesis reaction, and they produce one output or one product that is called M dash. how it is produced, how they produce the new molecule. I written over there. Please go through the text. The corresponding bit values of the reactants are compared. For example, the first bit value of M1 is 1 and the first bit value of M2 is also 1. If there is matching, in this case they are matching, then bit values of any molecule is copied to the product. So the first bit of the product will be 1. Similarly, compare the second bit of M1 and M2. So the second bit of M1 is 0. The second bit of M2 is 1. So there is no matching. So in this case, either M1, the bit value of M1 or M2 will be copied. So let us consider the second bit value of the product is also 1. So like this, all bit values of M1 and M2 will be compared and the bit values of M dash will be setting. Okay. And redox 2 reaction can be also applied in this way with two reactants M1 and M2 to produce two products M1 dash and M2 dash. You might have studied about the genetic algorithm, binary encoding of process. So genetic algorithm also follows this type of encoding process, binary strings. Okay. Then similarly, you can apply binary encoding process for displacement reaction. And finally, we have to update the reactant. So the reactant updation is similar to your reversible reaction. So I use another term, enthalpy. Enthalpy means the total energy associated with a molecule or reactant. So the total energy means kinetic energy plus potential energy. Or you can assume this enthalpy is nothing but the fitness evaluation. So if the new reactant has a better fitness value compared to the previous reactant, then the new reactant will be considered. It will be added to the reactant pool and the previous or the old reactant will be discarded. Right? So it is very similar to other optimization algorithm, how to update the reactants or how to update the population. In case of a genetic algorithm, we are using the term of population. But in case of a chemical reaction optimization, we are using the term reactant. So reactant are nothing but a set of molecules. Just like your population is nothing but a finite set of chromosomes or individuals. Right? And as I told you, you can assume the maximum number of iterations as the termination criteria, or you can assume the minimum error value as the termination criteria. Okay. Then we can summarize the whole discussion in the form of one algorithm, that's called your chemical reaction optimization. I used the term ACRO. Actually, you can remove that A. A stands for artificial chemical reaction optimization. Simply, you can use the term CRO. So it starts with reactant initialization. I wrote there set reactant norm. That means reactant number or the number of individual or the number of molecules. Then initialization of the source space, you can use binary random initialization. Then evaluate the enthalpy or the fitness of each reactant. Then within a while loop, you can apply different chemical reactions based on different probabilistic value. Right? So it is not mandatory to apply all the chemical reactions on a particular reactant. Rather, the type of chemical, the type of chemical reactions will be decided based on a probabilistic value. For example, if the probability value is less than 0.5, then you can go with a decomposition reaction or a redox reaction. Else you can go with a synthesis reaction or a displacement reaction or a redox reaction, a redox 2 reaction. And finally, apply a reversible reaction for updating the value or updating the fitness of your reactants or updating the reactant pool, then stop at the equilibrium condition. So what are the specific advantages of a CRO? Usually, performance of an evolutionary optimization algorithm varies from one data set to another. So there is all these evolutionary optimization algorithms comes under stochastic method. Stochastic method means their outputs are not deterministic, means their performance varies from one data set to another. There is no single optimization algorithm which can be applied to get optimal output on n number of data sets. So actually there is a theorem called pre-launch theorem. So there is no single algorithm or meta heuristic which can be applied to solve all type of engineering optimization problems. And the efficiency of an algorithm depends on the trial and error method. And the bottleneck of an evolutionary algorithm is how to fine tune the control parameters or the algorithm specific parameters. For example, your crossover, how to decide which value of which crossover value, crossover probability value and mutation probability value will give optimal output. So the performance of a genetic algorithm depends on the setting of crossover probability and mutation probability value. So that is a bottleneck of a genetic algorithm. But in case of chemical reaction algorithm, as I have shown you, there is no algorithm specific parameters or control parameters. So if there are less number of control parameters, then better will be the optimization algorithm. So I don't claim that chemical reaction or optimization is the best optimization algorithm. Rather, I might claim that it has superior performance compared to other algorithms in terms of quality of a solution as well as convergence rate. Right? So these are the major advantages of CRO. Like CRO, you might have studied teaching learning based optimization, TLBO. TLBO also does not necessitate any algorithm specific parameters. Right? So if there will be no algorithm specific parameter, but still the optimization algorithms works better, then it will be good for the users. Okay, so let us have a short break of 5 minutes. Now the time is 6:10. So again, we will start 6:15. Okay, let us resume. So I hope I'm audible to everyone. So there was a question from
yes, sir,
one
you are
participant
audible,
that,
sir.
yeah, thank you. So I found there is a question from one participant that whether chemical reaction optimization can be used for feature selection or not. So the answer will be yes, because just like other optimization algorithms, CRO can be used everywhere for any kind of engineering optimizations. But so far, I don't have a practical experience on application of CRO on feature selection, but it can be used. Okay, so uh, we have been discussing about higher order neural network plan as well as chemical reaction optimization, right? We have used the basic concept of chemical reaction optimization, the algorithm, the flowchart of CRO, advantages of a CRO. Okay. Next, I'm going to show you how the chemical reaction optimization will be applied on plan. First, before that, I will show you one application on plan, application of a basic plan using back propagation algorithm, right? And after that, I will show you the implementation of a CRO plus plan. I mean the hybrid model, how CRO can be used in the plan. Okay, so if time will not permit, then I will show you the first part. I mean the basic plan applications on financial forecasting, and tomorrow I will show you the CRO with the plan. Okay, so before that, let us discuss about the representation or encoding process. Okay, so once again, I want to show you the diagram of FLAN, functional link artificial neural network. Yes, this one. Or a more simple diagram is this one. So here, what characteristic or properties of a plan need to be optimized? As I told you, the input is given x1, x2 up to xp. And you can decide your functional expansion block. Means whether you have to use trigonometric plan or Chebyshev or Lagori or Legendre like this. And how many number of terms you want to generate, you have to decide. So all this process comes under input, right? And then at the neuron, at the summation unit, where I wrote sigma here. So here you need to calculate weighted sum. So weighted sum means the multiplication of input with associated weight, xi wi, right? Then you have to calculate the error. As for the error, you have to update the weight as well as the bias. For simplicity, I removed the term bias. Only I am using the term weight. So here, training plan means finding or updating the weight of the network, right? I mean, find the optimal weight and bias set for which the error will be the minimum. Now it is a minimization problem. Okay, so what we need to optimize? We need to optimize the weight and bias. We need to update the weight and bias in it will generate the model or the network will generate lowest error. Okay, so let us focus on how to optimize the weight. So updating weight means optimization of weight means this is the optimization. This is a minimization problem. And please remember, we need to update or optimize the weight and bias. Okay, so in my application, I optimize the weight, bias, as well the number of expansion unit. For example, if you are using trigonometric functional expansion, then how many functional expansion unit use? 3, 4, 5, 6, 7, like this. Okay, so the first part of the individual or molecular representation will be expansion unit selection bit. Okay, means how many number of trigonometric functions will be used so that the performance will be better. And in the second part, so in the middle part, we represented the weight set W1, W2 up to Wm. So here the weight is nothing but a binary string only. It is not a matrix, because there is a single neuron and the bias is B0. So this is the molecular representation. Or if we consider the chemical reaction optimization, for optimizing the weight and the bias of a plan, you can visualize this diagram. Please, for 1 minute, please have a look on this diagram. And if you are getting any difficulties or doubt, please ask me now. So if you understood, so let me go ahead. Only it is exactly the same plan, but only the difference is the weight and bias are adjusted by using CRO. Okay, that's why you can consider that this is a hybrid model. Then CRO plus plan process, how it computes the output. Given a training set XT and associated weight WT, compute model output Y cap, and the objective function is minimize the sum of error. So here error is Yi minus Yi cap. Yi cap is the model estimation or the network estimated value. Yi is the true value. Find the difference, take the square, mean squared error, MSE. And the objective is to minimize the value of this error. This is the algorithm for CRO plan. Okay, now let us go with the one application, how the plan can be applied for financial time series forecasting. And second part, I will show you how CRO and plan can be applied on financial time series forecasting. Okay, so this picture represents the closing prices of DJIA, Dow Jones Industrial Average. So this is a stock market, and the blue line indicates the pattern in which the value or closing price value of the stock market changes. So you can find a lot of irregular patterns in this graph. I mean, the closing price of this stock exchange DJIA fluctuating frequently. So there is no regular pattern, right? I mean, the curve or the graph is highly non-linear. It is not changing or moving in a linear fashion. Are you finding any straight line in this curve? Absolutely no. Right? So since the pattern is changing very frequently, since the pattern is very or highly non-linear, then it is very difficult to forecast the future value based on the current value using the mathematical models or statistical models. So many mathematical models are available for financial time series forecasting. Financial time series forecasting means forecasting the value of financial through the observation of current and past value of the time series. Right? So as I told you, different statistical mathematical models are there. Have you heard about the model ARIMA, ARIMA, autoregressive moving average, or GARCH, or simply your least square estimation, LSE? These are the statistical methods, and statistical methods are very much capable to capture the pattern associated with linear kind of data. But this kind of data, this is the real price. This diagram I copied from internet. So this is data. But this kind of real data showing high nonlinear behavior, chaotic behavior. That's why statistical models may not suitable to capture the patterns followed by this data. So non-linear models like your artificial neural network, or more specifically higher order neural network like PLAN, are more capable to capture such non-linearity data and to forecast future data. Okay, so these are numerical closing price values. These values are shown in this diagram, but these are the numerical values. Right? So the data set consists few columns. Forget about the date: open price, high price, low price, close, adjacent close, and volume. During a financial day, these data are captured. So what are the data? During a financial day, I mean the stock market when starts its operation at 10 o'clock and stops at 5 o'clock or 4 o'clock. Then in between these, what is the open price? What is the highest price, lowest price, closest price, and volume? So in my applications, I considered the closing price. Based upon the open, high, low price of previous or past dates, how to predict or how to forecast the closing price for the next day or next to next day, like this. So this is called your financial forecasting. So I request you please go through few literatures, and I wrote so many articles on each application. You can follow my articles also, and if you have any doubt or if you want any help, you can contact me. Right? Then the next question is how to use this kind of data to feed the neural network, or specifically the plan. Okay, so there is a specific method to generate the input from the original data set, that is called your sliding window method. On the top, you can see, you can consider, this is the original time series: x1, x2, x3, x4 up to xn. I mean, x1 is the closing price for day 1, x2 is the closing price for day 2, like this. Xn is the closing price for day n. So it represents a time series, or you can say that it is a financial time series, FTS. Right? And from this time series, this graph is not a time series. This curve shown on this graph is a time series. Right? And from this time series, how to generate input for the model? Let us have a slide window method. Let us consider one window whose width is 4. So in the first movement, the window covers 4 values: x1, x2, x3, x4. So these 4 values are used for training, and they are used for input, and x5 is the real output, that is called your yi. In the next step, move the window one step right, so it will cover x2, x4, x5, and x6 will be your target. Like this, let us move the sliding window on the original time series to generate training patterns or data. So for example, let us consider the first 3 sets as the training data and the immediate set as the testing data. You might have heard about the term training data, testing data. So these are very common terms related to your machine learning. Right? Similarly, let us go with 3 patterns or 3 rows for training plan, and the 4th row are the testing. Okay, so this method is called sliding window method. Another very common method is there. You can straightforward divide your data set into 80-20, 70-30 like this. I mean 70% data for training and remaining 30% data for testing, or 80-20 or 90-10. Another very common method is there, that is called your k-fold cross validation method. But those cross validation method and a straightforward method 80-20 or 70-30 is not suitable for this kind of a financial data. It's a time series data, and to decide the closing price for tomorrow is highly dependent on closing price of today and few past days. Okay, so in this way, let us generate the input patterns. And what will be the performance metrics? Let us consider the mean absolute percentage of error as the performance metric. If the MAP value will be closer to 0, then the model performance is good. Okay. Now, let me show you the implementation or application of a plan for financial forecasting. Then second, I will show you how to implement plan and CRO for financial time series forecasting. Okay. So let me go to, I implemented all these things in a MATLAB environment. So if you are familiar with the MATLAB environment, then it is good. I hope my screen is visible to everyone. Now I am showing the implementation of a functionality artificial neural network for financial time series forecasting. So the method or the model is FLAN, and application area is financial time series forecasting. Okay, so I hope my MATLAB screen, my MATLAB editor is visible to everyone. So line number 3, it is the input, it is my data set. Okay, and I divided the data set into training as well as testing. So I used a term called a target. Then I used some parameters alpha and theta. They are associated with the plan. I will decide the training length, means how many number of data will be used for training. Then how many number of iterations, as well as from which day you will start the forecasting process. So these 2 lines are for initialization of weight. I initialized the weight values randomly. So I used W equal to rand with some dimension. Okay. So I started my from here, and I updated the weight using some principles. Planned the computation theoretically. Now the computation is I am showing it is programmatically. So I calculated a delta, I updated W like this. So if you are interested, I will share this code with you. Later you can work on this. Okay. So here I am calculating the final output. Then here I am plotting the outputs. Okay. So let us start running this algorithm. So it is asking me enter length of input data. So let us use 5 number. Then press enter. It is asking training length. Let us use 3 number of rows as the training length. Input the number of iterations. Let us iterate for 50 number of iterations. From which row you want to start? Let 10th row. And press enter. Yeah. So my output screen is visible to all or not? Is it visible? One figure. Are you able to see one figure on your screen? Any response is there? Whether it is visible or not? I executed the code and on the screen I am getting one figure. Are you getting that figure or not? So I used the data for month of January, and the red stars are the original closing price and the black stars are the model predictions. So you can see more or less the model predictions or estimations are closer to the actual ones, red ones. Okay, but still it is not able to capture the non-linearity because the model estimations are not very much closer to the actual ones. So let us execute the algorithm once again with different values. Let me clear the screen. Enter the length of input data. Let us use more data, 10. Training length, let 5. Iteration, let 50. And let us start from 50 row. Are you able to see the graphs? Still it is not good. Okay, so compared to the previous graph, the quality of this the quality of this forecast is inferior. So let us have another. Let us use 5 number of inputs. Training length is 6. Number of iterations, let us use 20 number of iterations only and starts from 10th row. Yeah, more or less these forecastings are better than the previous. Okay. Any questions? I'm not getting any response. So I hope everyone is there, but no one is listening. So can I have a response whether my screen is visible to everyone or not?
Yes, sir.
Is my screen visible to everyone? Are you there or not?
Sir, it's visible, sir.
Okay. So this is implementation of a plan, financial time series forecasting. Okay. So here I am not using any optimization algorithm. Rather, I am using the traditional back propagation algorithm. Okay. So next implementation, I am going to show you how to implement a CRO. So I changed my editor. So are you able to see the stock index forecasting using chemical reaction optimization? Here, in the previous implementation, I used interactive program, but here I fixed it. Let us use the window size, that is called your bed length of 5 and the training length of 3. And let us use one data set that is called TAIEX, TAIEX. I mean, this is the stock index of Taiwan. And I used the normalization method. I used sigmoid normalization method. So this step shows that normalization method. One more function is there I used for normalization. Then, as I told you, there is only one algorithm specific parameter called reactant number. I fixed it to 50. Let us go with the 50 number of initial reactants. Okay. Then maximum iteration, I fixed it to 200. And I used the sliding window method for generating the input patterns. Then I fixed the training data here, training target here, similarly test data here. Okay. Then I applied different chemical reactions. So this while loop represents application of different chemical reactions. Okay. For example, see, if the probability value is less than 0.5, then generate another random value. If still it is less than 0.5, then apply decomposition. Otherwise, apply reduction one reaction. I shown you one algorithm, one flowchart also. The same algorithm or the same flowchart I implemented here in the form of a program. So I highlighted different chemical reactions. Okay. Then the training process goes on and the testing process goes on also. And I used adaptive training. So after the first iteration, I reduced the number of iteration to a very small value 5. This is called adaptive learning. So let us skip this terminology, but this is the one of the major strength of this algorithm. Then find the error and finally denormalize the values and plot the graph. I mean, actual versus estimated. So let us execute this code. It will take you few minutes to get the output. Please wait for a few seconds. Yes. Now you can see on your screen there is a figure. The figure showing one red line and one blue line. Actually, the red line is visible because the blue line is very much coinciding with the red line. So I will show you a part of the figure. Let me enlarge the figure. I will show you the part of the figure so that you can able to visualize the actual output versus your model estimation. So let us display up to 100 number of data. Now you can see the red line is the actual closing price values and the blue line is the forecasted or predicted closing prices by CRO plan. Okay, so let me change to 500. Now you can see we can conclude that the model estimations or the forecasted values by models are very much closer to the actual values, and more or less the model follows the trend of actual closing price values. Okay. So, and the mean absolute percentage of error is 0.0115. I mean, only 1% error is there, and it took this much time to execute. So you see how the complexity of the model is the complexity of the model is very less, and the error generated by the model is also very small value. And if we change the value of the reactant, as I told you, there is no model specific parameter or algorithm specific parameter except reactant number. Let us change the reactant number. Let us make it only 10 reactants. I made the reactant number 10. Okay, let us see the output. Yes, now we can see the output. So let me show you for 100 number of data only. Now you can see, though the model follows the actual trend, but still the deviation is bit more compared to the previous implementation. If we make it 10 number for 10 number only, you can see for 10 number of data, you can easily visualize the pattern. Okay, and now you check the error. Now the error is 0.1570, but earlier the error was 0.0 something, 01. So only the parameter which affects the performance of the model is reactant number, only one. So let us make it 100. Please wait for a few seconds. You can see the implementation, no other specific parameters like your crossover probability, mutation probability, or selection value, nothing is there. Only the iteration number, which is very common to all other optimization algorithm, and a reactant. Yes, now see the output. Now first see the error value, 0.0067. So compared to the previous executions, now the error is very minimum. Okay, with the 100 number of reactants. And now see the graph. Let me show you with the 100 number of data only. Now see. Okay, so with the 100 number of reactants, the model gives very lower error, that is 0.0067, but the computation time is a bit more as the number of individual or reactant is more than the earlier applications. Okay, and now let fix the reactant number with 100 and let us change the iteration number. So here is the maximum iteration I made 100. So let us make it 50 or 10. Now let us compare the output. So there is no specific rule to decide the number of maximum iteration So it is it can be decided with a trial and error method. Yes. Still, with 10 number of iterations, the error is 0.0096, and the forecasted values are also very much closer to the values. More or less, it is following pattern of original data. Okay. So, any question? Let me summarize. I explained you simply artificial neural network. Yes.
So thank you very much for your excellent lecture. Actually, I'm a financial engineer, and this, particular, talk from you is very much relevant to my discipline.
Yes.
So you have really made my day. Thank you very much, sir. Thank you very much. Sir, my
Yeah,
humble
thank you very much.
Okay.
Yes.
Pleasure is all mine. Sir, actually, I'm humbly requesting you, sir. It's not only artificial neural network, but there are, so many neural networks that we need to use in the real world scenario. So that is why I need to be in your touch through email and WhatsApp. Would you please be kind to share your email address and WhatsApp with us in the chat box? Okay. And secondly, so would you
Yeah,
please be kind
sure.
to share us?
I will share my.
Thank you very much.
Yes.
Thank you very much. And would you please be kind to share some good books on this
Yeah,
particular neural
actually,
network thing,
yeah.
their application for, or time series data? Thank you very much.
Yes. Yeah, thank you for your feedback. But let me clarify. Actually, the time duration of 2 hours is not sufficient to explain financial time series forecasting. So I skipped
Yes, sir.
so many things of financial time, basics of financial time series forecasting. And if you are
That is
interested,
why, sir, I'm
then
humbly
we can
requesting
work.
reference
We can have a collaboration.
and reference book. Thank you very much, sir. Thank you very much, sir. Thank you very much. It will be my excellent luck and opportunity to collaborate with you, to work under you, to learn much more from you. Thank you very much, sir. Thank you very much, sir. Thank you very much. Please be kind to share your email
Yeah,
address
thank
and phone
you,
number.
sir. So, yes. I'm sharing it. And actually, right now I'm in India for a few days. That's why I don't have a proper setup also. I'm using mobile data, so it is very slow. Some constraints are there, but still, thank you all participant for your patience. So I shared my email ID in the message box. It is sharatnayak234@gmail.com.
And WhatsApp number, please, sir.
Yeah, I'm sharing. That is India number.
Very much, sir.
94384 and for more information you can please contact Dr. Sanjay Kumar Ponda as well as Dr. Ma'am Manjubala Bishi ma'am.
Okay, sir. Thank you very much, sir.
Okay.
Thank you, sir.
So
Hello, sir.
thank you all.
Thank you very much.
Yeah, Sanjay sir, thank you.
Yes, sir.
And if you don't have any questions, so let us stop here with the permission from Dr. Sanjay Kumar Ponda and Manjubala Bishi ma'am.
Yeah,
So
sir. We'll stop here.
let us stop here.
You have another session on Wednesday. Wednesday, 3 to 5
Yes.
session. So you will handle that, sir.
Yeah, thank you, sir. Thank you. Thank you all.
Thank you. So thank you, everyone.